I believe all of you are techie, so who am I? So basically, I'm an electronics developer. I tinker around with firmware and hardware basically. For both professionally, I do it for work and also for my own curiosity. So particularly, I do embedded software and hardware consulting, and then I'm also open source contributor to various projects. But recent years, I've concentrated all my work on Zephyr RTOS, so that's the area I'm focusing on working and also open sourcing work. So just before I go into the talk, how many of you know what is RTOS, real-time operating system? So quite a number of you. So okay, cool. How many of you know Zephyr RTOS particularly? So I just see two hands, so which is good. I can just give a very quick brief of what Zephyr RTOS is about. So Zephyr RTOS is a real-time operating system, just like any other RTOS, but it has added some new features. It's kind of like a leading edge new RTOS, open source in nature. And these are the areas I think every one of us will agree where real-time operating system will go on. Like you can see industrial IoT and asset tracking, all this area. And I think we have gone through the era that, between this, if we talk about many years ago, people will be talking about, oh, RTOS or bare metal, RTOS or bare metal. Like, some people will be argue, I will do bare metal. But I think today, many of us agree that any embedded system mostly will be running some form of RTOS, regardless of whatever application it is. So that's where I set a definition. So where Zephyr RTOS lies, basically. So Zephyr RTOS is basically, they have few points, the main points that they target. One is it has to be small, so that it can run on any target. Anything with less than 8 KB flash, 5 KB RAM should able to run Zephyr on a very minimum, at least minimum. And then yet you want to be more powerful. You just don't want to offer only just like other RTOS, just a scheduler and so on. It's very boring, or it's very common. So you have to be scalable. You want to handle SMP, multi-processor handling, and all these things. So that's another area. And then you also want to be flexible. The kernel, basically the kernel supports more than 450 boards, multiple architectures, and so forth. And I think big area that we talk about RTOS and IoT, you want to go to the internet. So if you want to go to internet, you want to make sure your code is, at least secure in nature. It has some, vulnerability check and open source in nature, I think. So these are the area basically Zephyr covers. So on a high level, if you look on the right, you will see on the box what Zephyr offers out of box. It offers a third-party library all the way until the hull, so that you can integrate vendor hull into your Zephyr and able to use Zephyr naturally. And where Zephyr particularly fits, or it's a unique proposition, is that wherever Linux doesn't fit, basically, Linux might not fit on an MCU because Linux is big, but Zephyr can fit in there. And it works. It uses a lot of philosophy or strategy being used in Linux into Zephyr. So that's why I think people, started to get interest and started to work on. And it is highly portable and secure, like what we talked before. Just like Linux, right? You can take a Linux kernel, run on an ARM. You can run on a RISC-V and all sort of things. Different boards are supported. The same things are here. Particularly if if you've been working on Linux kernel, there's something called device tree, kconfig to do all these magics behind it. So that's what being happened in what we call MCU world itself. So I think I'll just give a very brief introduction what Zephyr is all about. Now particularly and about this topic is why Zephyr and RISC-V. What Zephyr uniquely offer for RISC-V, or how the support is like and so forth. So the first point is both are open source in nature. Anybody that's supporting RISC-V, I think inherently in their mind is like they want to be open source. Like the silicon is already open source. Whatever things the IC is open source, and you don't want to run a closed source software on open source silicon or ISA basically. So that's I think a good combo. And then the current state of affairs in Zephyr is that all common ISA that RISC-V supports is already there. So I think the standard thing is everyone, if you look at the privilege set, there's this RVM32 IMAC, the basic instruction set is fully supported, and there are also some advanced extensions are already supported also. So basically, you can say pretty good, at least ISA level support architecturally, it's quite good. And you may ask, what about some other standards that RISC-V already set? Like we have PILIC, the interrupt controller for the process basically. So that is PILIC is a standard interrupt controller by the RISC-V Foundation, and that is also supported. There's a driver already basically. And also for machine timer, so all your ticks in RISC-V you handle it using something called C-Link. So C-Link also the driver is supported. And the fourth point is because of RISC-V is so modular and all like modular in nature, you want your software to be modular also. So that's where I lay down the point. Zephyr is structured and modular, so it's very nice fit. So this is a board I did some porting. Basically, the boards that we're going to be hands-on. So I just want to give you an idea, what really been happening behind the scene at a high level. So basically, we say that this is a SOC RISC-V 32 Phoenix Sapphire, and we are just enabling all the instruction that it supports, so that the ISA level knows what are the instructions are supported, and the entire kernel, or basically the Zephyr ecosystem, knows what are the ISAs being supported based on the SOC. So you can see I'm just telling RISC-V ISA IMA this process supports. So, and then when I do that, because Zephyr is so modular in nature and the build system is inbuilt, CMake can start reading all this configuration file. So it started knowing, okay, if ISA external A is supported, when you do a build, pass this A flag to the compiler basically. So you don't have to configure all this thing. It's all automated in nature. And then one more, just for another example, like any of you know kconfig, if you enable like config FPU, then the Zephyr know, okay, if I enable FPU, then I need to give the -d or FP or whatever it is. These are all passing to the compiler basically. So it doesn't stop there, the architecture level code. So this is one example where the same configuration is pulled into my source code basically. So what you see here is if defined config RISC-V ISA RV32E instruction is enabled, it does a different kind of code. You can see it is accessing register differently. If it's not enabled, it access differently. So all these things, naturally it's on the ecosystem basically. Okay. So this slide basically, I thank Phoenix to give us the opportunity. They provided us a FPGA and RISC-V core to basically play around. So just give a quick introduction. So it's the most efficient FPGA and time to success. We want you to get your open source RISC-V ISA easily emulated into a FPGA and turn into a kind of a RISC-V core and start working on it. And what is so unique is they already have a kind of like a manager, so you can easily configure whatever peripherals you need, together with RISC-V, and you just generate it. The RTL is generated for you, and the RTL can be loaded into your FPGA and turned into from FPGA it becomes basically a RISC-V core. Okay, this I think some important point is it's RISC-V. All of us know open source scalable and all these things. But what Phoenix offer in site to site is all these things like what I mentioned earlier similarly. So, any question before we jump into the workshop? So, if no question, we will jump into the workshop session. So before we jump into the workshop session, I would like to tell what exactly the some high-level process going on in this workshop. So due to time constraint, we have loaded a bit stream on your board. We have generated the RTL and we have loaded the bit stream inside it. So basically, when you turn on your FPGA, it just acts as a general MCU basically. Pretty clear? So what we're going to do today is we have a cloud machine for you. You have a login ID and password and all this thing. You can log into that and start doing a hands-on build session. Like how we do in software hello world. We want to build a Blinky session and get your hand around with Zephyr on live session. So that's what today's a challenge of all of us, because I think inherently when you talk about embedded system and things like that, people will tell you to install a lot of tool chains, set up all the things in at your home or before you come to the workshop. But what we are challenging ourselves and we want you to join together is today do it hands-on live on cloud and easily install and see. So we have three prerequisites. So basically, first thing is you need to download the workshop guide so that you can follow the guide later on. So I hope you can see the link. It's a short link. If you put the link, you will get a PDF basically.
You may take a picture of it. Use it later.
Yeah, if you guys need some time to type it, you can take a picture. It's a good idea. Okay, and then the second thing is to check is you need these three items with you. I think you should have, because we have already put on your table, done. Then the third thing is you need to have the credentials. Like all of you have credentials.
And just to ensure you're on your own hotspot, some of the phones are getting blocked. So if you have a hotspot, please connect instead of the Wi-Fi.
Okay, everyone pretty good?
How long was that? Or it's hot. I heard it's 3 p.m. Someone has to leave, so I take over the job.
Yeah. So I think all of you can turn on your board and all this thing. Just make sure that you have a switch on the board. Actually, there's a small tactile switch. If you turn it on, you will have a lights on it. Just make sure that you have the LED, something comes up, so that your board is powered and your USB is connected.
There's some smoke here.
What's the color of the smoke? Is it blue or green?
Sure.
So everyone got the credentials basically.
Just looking at the
And I didn't check it.
Login as which one? So login as GitLab?
So I guess everyone got the credit.
Yeah.
Everyone got the. Hello. So okay, may I get a raise of hand who's using Windows and who's using Windows? Okay, we have some hands. Anybody using Linux here to try the hands-on? Okay, cool. Open source. Okay, cool. Mac is unfortunately not. Yeah, it's a mess. So for now, no. So okay, the guide covered both, but something to take note is if you're on Windows, you have to do this thing. What we have provided on Windows guide, you need to install this ZDIC so that you can install this particular driver actually. So you just have to follow this guide. You go through all these interfaces, whichever you see titanium TI-60 Phoenix. You just have to replace it with this WinUSB driver. And next is, I think, I believe all of you is trying to log into the labs. So I guess all good, right? So good. So you can just launch the dashboard now, so that you get this page. And under the My Labs, you can just expand it. You'll see something called Machine Labs. Okay, and then once you click the Machine Labs, you'll find something called RTOS Lab for Zypher. Okay, another status check. May I know how many of you already come to this point where you can see the RTOS Lab for Zypher? Not yet. So let's give some time probably.
So you just have to go to My Labs and
Yeah, just say the.
go to Machine Labs and RTOS Lab for that.
Okay.
So you just go to deploy. Yeah, deploy. No, he's already said.
Okay, RTOS dashboard.
Just go for this. And then
Yes, I use it.
it's something like that. So I get the claim.
So there is an unticked account here. Basically, is which not be used. You will not know.
Is that the thing? Or you have to go to one?
So
Is that only the one? Is it?
One day too much is like, okay, I'm just following it, see what's it. But if you want to use this, I could just go out.
I think I heard one of you using Mac. No worries, if you're using Mac, you can't flash to the board, but at least you get the experience how to get the binary at least on Zypher.
I can always come to the Linux guys. We will sort it out.
Choose any.
Back is back. Okay, now
So anybody that already got until this step, you can click deploy so that the machine, Linux containers spawn up for you. Pre-configured toolchain, Zypher, and everything is in it.
Then you plug in here anyway. I just.
So where is it being deployed? When you deploy, where is happening?
So basically, when you deploy, it's on the it's running on a cloud machine. So a container is spawning up with all the tool chains and Zypher in it. So once you have put the deployed, basically it's just like turning on your machine. The container just comes up, and after like a minute or so, it takes like the page will reload. Once the page is reload, you can find on the right hand side something called code. When you click on code, it will prompt you to something like, do you want to launch? Something like this. And when you click launch code ID, it might even ask you whether you want to enable pop-up because it wants to open up in another tab basically. and it will ask you password. So where do you find the password is you go to your dashboard previously. You'll find password, and the password is on the last field, something called code server password. And you see something like a password viewer on the right icon. You press that to see the password, and it should copy the password also. You can copy the password if it doesn't. So if the password is copied, and you just click OK, you should get a full-blown VS Code. Like anybody familiar with VS Code, it just comes up on your browser. I do see some people already got to the point on their own. They have able to build their firmware.
I should have go to 2-1. Sorry, I should have from 2-1 go to 2-1. 2-1 will be 2-1 people of 2 already. I need to learn how to swap over the software.
Okay. So I think most of you is at the point where VS Code is up, spawn up. You can see like ID is there. It's a good sign. So the next step is you need to any ID you work on, you open up. It's just ID. You want to go to your project folder. So we have set up this FO project folder. It will be something called Phoenix Cipher, and then you need to put a slash cipher again. That's where the cipher. You can see on the top. Just after the username, you add a slash and then Phoenix Cipher slash cipher, and then click OK again, and the project will be opened up on ID. To go to the drop down, you go to File on the sidebar. Which drop down you want? No, it's already opened. Oh, you opened wrongly. Okay.
Okay, my one.
Yeah.
File.
Maybe.
That means 10 minutes.
So you have to, I think, open
Should
one
I?
directly.
Oh, you have to follow your heart.
The one more.
Yeah.
Maybe.
So if they do something that
Oh,
yeah.
open
Open folder.
Maybe I'll go 5.
The same, but you just have to open this folder.
Well, and
Yeah, okay, yeah.
Yeah,
That's
yeah.
what I thought that
Yeah,
was
yeah.
right.
something helpful or 25 minutes.
Oh, one more. Okay, this one.
Keep
So-
showing.
Alright.
Just like
Okay, I think most of you now is on the Phoenix Cipher slash Cipher, so it should be good. So, like you need basically a terminal to interact with Cipher basically, and there's so to do that now you have to go to the same sidebar and go to terminal and click new terminal, and you'll get a terminal on the bottom. This is just some IDE guide basically for now. So the thing is now we need to get the ID just comes up for the next step.
streaming feed. string results. This is the control point.
Oh, there, yeah.
It's checking the configuration.
Okay, so this is your generic Linux kind of bash, bash terminal. Like any of you work with Linux, all the ls, mbcd, all this command just works out of box. So now, if you go to the basically the guide we have provided, the one on the bolded is a command to do that. Let me just explain what this command is doing. Wes is a helper tool built for Zypher. So whatever you want to interact with the Zypher kernel, you need to use Wes. It's like the front end of the kernel. And -p means it's a pristine, so that you want to clean the build every time you do some build. So that's what I give a -p, -p, and always. And -p stands for board, what board you want Zypher to build or work with. And the board that currently we are working on is called Titanium TI60F25. And then the project that we want to build. So one of the cool thing about Zypher is also the sample is part of the kernel board. So you got the sample basic blink key there. And all you have to do is click enter. And if you click enter, the firmware will be built, and it will have in a certain folder that I'll tell you later.
Delay is pretty high.
But I guess we wouldn't be able to refresh. But right, the thing is, arrows.
I have also turned on. I don't know how this works. If he asked me to type in this where and how, yes. Okay, please, that's how it is connected to this one. Okay, you should remind on web. So make sure he or she has the connection.
So I do see some people already got the info, like how much RAM it is using and all this information. So that means build is done and your binary is ready. Let's just get more people before we go to the next step.
然后连上过后，然后就是他们就进入这个网址。
对，专门开一个是说别的这种对。
之后好，
反正你可以都在文森里多少钱，就我给他的下一个我看下一个话，自己看两个书，他寄过寄的包，寄的笔记。我们刚才讲说什么用？
对，就是一些 permission， 然后买的，
然后他买，然后他这个这些
要允许。
OK，
对，就这种。
反正我这样说，他看见我告诉我说要 S3 好像有秘书，
这个步骤这是应该是我这里有问题，有一个平台，直播平台有些问题，主要就是每结束过后，你就把这个秒，
把谁灭了，全部灭了。
对，秒，就把自己秒，
把这个
就播放这个。
一直都等，对，一直都等。还有一个，
对，还有这个音乐，
第一个，对，
必定到，
对，对。
对，
OK， 放一个，可以，
然后就把它
So where is it hosted, right?
这个东西对，这样
Yes, self-hosted.
OK，
Where is it physically?
然后弄完回来之后，
是不是跟
插上去之后，应该就有一个东西跑出来了嘛。
对，就有这个东西跑出来，
然后一直录之后，就是
它这个东西跑出来，你还得add to string，
对啊，这个也是可以。
对 add to string 过后，你就会看到类似这样，
OK，然后上面这个那个这边关掉，这边关掉，
然后就把
你可以不关掉，
这个是关掉，
这关掉是按钮键，
音乐
还是关掉，
对这个关掉，
按钮是按钮键，
对按钮，
一个录点按钮键。
Cipher it is like.
然后它会是这样子。
You can actually see how better to do that.
就是比如说我是那个
对，我播后面的 hide，
对，它就会变海，因为它现在是
Bro, ask
对的 hide，对，
然后对把它关掉，然后把自己
mute 哦，这前面的 OK， mute 先 mute， 对，然后开一直录放音乐，然后用完，回来之后连 S string，S string 完 mute 解掉，然后开，然后把那个关掉，把这个关掉。
So I guess most of you got till the point you got the build done. Like you see some stats, how much RAM it's using and all. So the next step is actually to download the binary. So the binary is inside build. If you look for build folder or directory, and then you go to a folder called build/cipher/cipher bin. So you download the cipher bin. So that is your Blinky firmware that your computer built basically. So, and then to download, you just have to go to the file, right click and click download. Just make sure that you save it in a place that you can locate easily later, because we have to move these files around a little bit later in your local machine. The reason is your cloud don't have access to your board, so we do all the hard work and all the highly complex configuration work on the cloud, and we take the binary file, we bring it to your local computer, and we flash it to the board. So somebody actually got the Blinky up and running. What do you want? You have to right click and download. Okay, so that is basically on your computer, local computer now. It's on your download folder or something. So keep the file for now. So that's where the next step gonna come in.
Alright.
So let me check on few people.
I mean, I have it.
Like the JTAG interface. So I believe most of you downloaded the cipher.bin. Like how many of you got it? Like raise up your hand. Okay, we got most of you.
35.2K.
Okay, cool. So now this is the thing we need to. This is extra step for Linux only. You have to do a git pull currently, because we actually just did a live push on a rule. Basically, we missed the rule earlier. So you do a git pull now, you will get a new file coming into the thing on your cipher directory, the directory you are, the terminal. Just give a git pull.
I'm not very sure, right? Just as a regular user.
Yeah, git pull. Once you do git pull, this is only for Linux, okay? Windows is sorted out because you've done the Zadig thingy.
Oh, you need it because the bin has to be fixed for that.
No, so this step is to access on your Linux machine, to access your board. So this is like a driver kind of work.
Also from the browser is going to access a USB port.
Okay, not really. So let me just explain the step one by one. So we going to download this thing called linux.zip in a folder called flashy, and you need to bring to your local computer. To get the correct latest file, you need to do git pull because the file that in the container is an old file. It doesn't have one of the rules. If any of you know UDEF ADM, UDEF basically. So there's a UDEF script inside basically.
Okay.
So just do a git pull and download the latest Linux.zip. For Windows, you can go ahead and download Windows. No changes required. Yeah, pretty cool. So once you download it, you extract that Linux.zip. You will find you can open up on your terminal the current directory, and you do a sudo /usb driver.sh. And what it will do is it will configure all your things to access the board on your local computer. Like I mentioned earlier, basically, we do the build on the cloud, but we want to install to the target FPGA board using your local machine. I know, we have done that work inside using the GUI app. The first So just make sure that you do sudo./usb driver, run the script from the folder you extracted it, because that's how the paths are configured in the script. So that only will work basically. So you already run the thing. So for those who have already configured on Linux USB driver and all these things, we can go to the next step. So the next step is actually installing the firmware basically. So for Windows, you can just double click the flash. You will see something called flash. It's basically a batch file or whatever it is to run the script. You just double click if your board is connected, and if your Blinky file is on the same directory as where you downloaded the zip, where you extracted it, it will just load that Blinky on your board, and your board will start blinking if it's correct. Or on the other hand, on Linux, you need to open up a terminal and do how you run a script /flash.sh. So let's give time for this, and let's see how many of you get Blinky out. So I see another board is blinking also. When you on, the LED should be anything should be up. So Okay, cool. So I think a couple of you got blinking light. So basically that means you built something using something like a cipher. You got the binary, you brought to your local computer, and you're able to flash it.
Bro, can you go to the vestibule? Yeah.
So those that you are, those that already done, you want to go a little bit further up. Just say you want to see how shell works. You can actually go to the Blink folder, the same basic Blinky folder. On the project.conf, you can enable something called config_shell equal to y. Any of you work with Linux, it's very familiar. And the shell will be up, and technically you can connect to the COM port of your laptop and interact with the board. Like I think this is particularly my favorite thing about Cypher is that you get a shell out of box. It's pretty nice. Like you get like a shell application on RTOS basically.
我这有个家里他会是管理最好的口服理想，就是比较熟，之前来这边我跟他会称职场合，应该这才能但要做就是去大厂要去用去那种 internet 就是要其他地方去买点在这边的代理，是我们在这边就Chinese internet因为这样的就是这个上次几次也想到，一次也想到上本身。然后我这个因为没有关系，就是因为我在想，我想在强调什么，就是外在，所以没有就是没有的话，就是要第三个。因为我没这个看到那个人就是那就是顺便看他顺便文件很早，都新加坡都如果跟你不是在比较，有个人叫胡，知道现在比较胡在做第四方，我是觉得最近不太好。因为我的认识，因为我尝试做，我也没有，可能解析这个麦克，我知道这个，知道他被开始嘛，开始我有听过看到那个，就是没有在身边最近这种，然后我说出来，我有一个可能就是
Those of you who want to try the shell, you can see my configuration file. So you basically go to samples basic blinky project.conf. You just enable config._shell equal to yes, and you do the repeat again, the command again. You get a new binary and you install on your COM port if you have a serial kind of a COM port access. Like on Linux, I use minicom. You could interact with the board using a shell basically. So one point to note here is this is something very unique about Cypher also. You just enable something here, the build system knows about it, it builds some new source code, common source code, and it just injects inside your thing, and you get a new application. So this is, I think, pretty cool, right, for something like a microcontroller.
纯粹我个人认为就是走过一些，如果你自己做学习是一样的，基本上，可是如果可以不走学术，就真的是不知道方法。所以我是可以自己私域了之后看，甚至看参加。
都是我应该没有一个这种直觉，知道就是把它算出来，我觉得这是没有办法知道。
那这种把出来的读物是这样。
I just on the next I'm speaker to the 2:30 p.m. On the session seems not ended. So on the story, and can you enforce to stop the session?
Because it's controlling this kind of product. So I'm just taking 15 minutes. And download.
So I think to wrap up a little bit, we can say that most of you that got a board are able to blink, able to build, and have a hands-on session on Cypher. Because I know you can go and learn all this thing, but having a hands-on session is always good. Oh, this is how it works. You put your time here. In like 1 hour time, you did a build and blinky. So when you go back home, you can explore more at one stage. So any question, we can open for question also. Like if anybody have any question regarding Cypher, or are you interested to contribute to the journal or whatever it is, I'm happy to share. As of now, I can
放加个那个吧，你有这个。
Ah, yes.
By nature, it is already.
Okay.
So, guys, I hope all of you got some insights, especially interact with Cypher. And I'm so glad to see, we got a blinky up because this was our challenge also. Like, it was the first time we push FPGA, we push Cypher, and we push it live basically, like on cloud and all these things. So I'm happy to see it's blinking. I hope you are happy also. And I wrap up my session here, and thank you so much for attending this particular workshop.
Thank you.
Thank you so much.
So thank you very much. Please one more time, a round of applause for our speakers, Manoj Kumar. So thank you one more time. Thank you. So we get to keep the boards, right?
That you have to ask.
If you touch it, you keep it, right?
The boss is there.
Boss, can we have it, boss? Okay. Anyways, so let's get the next. Yeah. Thank you very much. Any questions? Anybody? Or you have already asked all the questions you need to ask? Yes, no, yes. So how much are these boards, by the way?
Yes.
This is a full set with a camera, display,
Oh,
and
this
all
one.
the connector inside. So it's about $300. I think all is sell in DGQ. So both a kit, component, all the buy from DGQ.
Cool. 300 Sing dollars or 300 ringgit?
US dollar.
US dollar.
Within a week. I think always available.
So one more thing is, if anybody want to think around on these labs or whatever, then the account will be still active for 10 days. Or if you need any information, you can find my email and ask us or whatever.
So also you could take my email. I have basically built labs. So I did it during COVID, and now like over 5,000 students are using it for different purposes. Me and Manoj has contributed recently, and we made Zephyr possible in cloud, and we are continuously adding a lot of laboratories. So we are trying to make something like AWS, but at a very low cost. So you could do everything online. You can host website. You can run any number of databases. We basically all services. If you have not checked in it, just go to the services and you could see MySQL, MongoDB, Redis, RabbitMQ. We got all open source in there. So it's all managed just like how AWS does, but on your own cloud. So if you have any doubts using labs, or if you need it for your personal use, you may contact Manoj and we can set up a account for you. But this demo account is still active for 10 days, so you could take one username and password and play with it. So thank you all so much.
Thank you. So thank you everybody.
wrote the stick, Raspberry Pi stickers. So if you want it, please come here to get it.
Edible. Not edible, right?
Yes.
It is edible.
I bring you stickers. Thank you. Thank you very much. So you're helping. So, first of all, thank you very much for coming here, coming to my session. It is, if you past 3 years since COVID-19, it is the officially and offline event of FOSSASIA 2023. Also, I'm leading a Japanese Raspberry Pi community and helping Raspberry Pi and the foundation and the Raspberry Pi training to helping their business in Japan and more lately helping the engineering business. Now looking for the good case in the Asia area, Taiwan, China. I checked it on the Explorer in 120 Raspberry Pi cluster to catch up on the 3D and the outfits. It is very good case. I talked to the person of India. If I talk to today, you've seen the press the release on the Raspberry Pi Foundation and the strong relationship with Sony Semiconductor and collaborating HAI solutions. Sorry, I can't tell the details, but I would like to talk that briefly. The collaboration is focus on the Raspberry Pi camera solutions. Even if the Raspberry Pi camera solutions are made by Sony, they use the Sony chip and the Sony solutions and all Raspberry Pi things are made with Sony. Now they go into the next stage to use a camera to recognize something for AI. Especially looking into the Sony cameras and running on Raspberry Pi. It is a tuning up for the Raspberry Pi things and more easy to develop the AI solution for developers. You know, the Raspberry Pi now release many more camera solutions. Lately, the global shutter camera to catch up to the movies or something. So it is now the collaboration stage to catch up something. To next stage even recognize something with Raspberry Pi 2 and analyze with AI. This is the next stage to the Sony collaboration with Raspberry Pi. Sorry, I will keep in touch with my Twitter to the next step. I think it is a game change because it is the AI solution is not so strong in the Raspberry Pi. It is a Jackson stages, but if now the Raspberry Pi and the collaboration with camera to compete with the Jetson. So it is game changes. I'm waiting for that. So it is game changes to next stage Sony and Raspberry Pi. And more, and some of you know in the AI solutions in ActCast. In ActCast tuning up for tuning up Broadcom video GPUs. It recognizes faster than we expected with TensorFlow. They originally using assembler-based programming. So they use the original SDK to the developer. It is container-based, but it is very faster than you expected. And there are many now many use cases. For example, they're using the convenience stores to recognize customers. They also using the zoo recognizing the animals, working animals move and animals activities. It is very useful. It is also very useful for that. But it is another solution that Sony the Raspberry Pi purpose, and they focus on the camera itself. It focus on the tuning on the GPUs to recognize faster with AI. It's not. It can be developed with about the AI solutions. Stay tuned. So I will feed for information, especially the AI developer to how to build something to AI solutions in Sony and the Raspberry Pi collaboration. And so show you explore Raspberry Pi website. Now you can see on the Raspberry Pi on the .com website. You see the whole home and the whole industry website in raspberrypi.com. Now raspberrypi.com focus on in a home DIY on the industry and the enterprise users. And more, Raspberry Pi also focus on the even ordinary education business for children. It is and now they have the Raspberry Pi project the things writing a code to itself and to learn the code children and more. They have also online courses for teachers to learn to teach code to the kids. They have been building something on the project and more teaching teachers to reteach the students who kids IT kids education. And more explore Raspberry in the Raspberry Pi official magazine to the articles some issues for that. They may be also use case for that, and they also have article for the the makers or key person in each area. I checked the Raspberry and my committee members like the issue for that and some more people Asian people I've checked writing about their project and lately I have packaging in the Qt Pi tablet project which is which made by Taiwan. This Cook tablet project inside computer module for inside, and they use open source hardware tablet. get Raspberry Pi sub-brand. It is good for a project or Asian area. And if you have any good project for that, please retweet your project to the Magpie. Magpie writer looking for good cases, especially in the Asian area. Because of the Raspberry Pi, Magpie is personally, some of you have read Magpie magazine. Almost use case from European area. But they sometimes they offer article, some other article for the Asian use cases, but still few. So if you have any good project, please retweet the Magpie to check to tell your project in detail. So Magpie writers could pick up your project and discuss with you about the project to write article on the Magpie. Now looking into some projects, Gormin Hub, it is audio project for Raspberry Pi. They are planning to some hubs for Raspberry Pi on the other board, and now they're evolving to Raspberry Pi audio solution. Of course, Raspberry Pi has all Raspberry Pi has purchasing audio vendors to build a Raspberry Pi audio hub, and now they release a couple of products you can see on their website. And I checked that. I'm very interested in this use case in the booth. Please stop by the FOSSASIA and the FOSSASIA and Expo booth. And I guess they have manual clusters using code. I'm sure it is used for the HP clusters, but it is used for the 3D snapshot. Using the 120 Raspberry Pi clusters. It is very cool project by Indian people. So I'm very interested. Plus, I will introduce the Magpie to be up to for this project. It is very cool project, I think. I think the project is good project is not so complex, not so difficult, you should focus on the good. You should focus on the project purpose itself, because I checked here for another example for that. It is I introducing cases on the today and today the alcohol parties in the night. I don't mind this party. This is a good use case in the Japanese winery, and it only measures the temperature and humidity. Because in this summer season in Japan, it is very humid and hot in the summer season. It harms and grapes itself. So they the buyer have to use the chemical sprays. But if he or she use more sprays, it harms the wine taste. So they should control they should control the spray itself according to the humidity and the temperature. It is only humidity and temperature, but it is good use for the growing and the grapes and so formally. So it is a good use case in the vineyard, I think. This is this use case were picked up in raspberry.com. And please check the website. You if you have a time. And more. I should tell you another use case. I really like to tell you one more. Sorry. Okay. It is another good case I introduced in the Raspberry Pi. It is it is on the it is Qt Pi in the project by the Taiwanese speaker named Pek Chen. It is a good, it is small tablet and embedded on the Raspberry Pi compute module hole. And more, he made a UI, and he works for Qt, and KDE based KDE the solution company. He built it UI to hold Qt Pi tablet. He also made many more Raspberry Pi based the computers and the pen screen and also pick up the Raspberry Pi on the website. You can see on the Raspberry Pi on the website.
I saw that one. I saw the website. Yeah, one with the case.
Yes. Yes. Oh, yes, it's a pen case. Yeah. He is a very cool people. He used to, he now is living in Germany, but he used to live in Japan, and he looking for what kind of things are good for invented for Raspberry Pi. So he has to write the pen case, and so for the pen skill, he can use the Raspberry Pi. So yeah, 7 minutes to wait. Sorry for that. Just looking what about the main screen to back on it. Issue. So I would like to also tell you the documentation about that on last 7 8 and the Raspberry Pi documentation And you see on the website, this website in detail, and you can see on the detail and the documentation for Raspberry Pi website. Not only raspberry.com and to build something in Raspberry Pi, but also in the raspberry.org to how to teach children to understand we are online or something offline to something. And Raspberry Pi product information portal is useful on something like hardware information about that. For the documentation and the accessories and the hardware specs, so you can see on this website. And I just introduced the Qt Pink chain, and the Raspberry Pi, powered by Raspberry Pi, the substitute brand for you can use on the product. And so you can see a Raspberry Pi portal, you can see Raspberry Pi, powered by Raspberry Pi product catalog. You can see the products here with a Raspberry Pi. And if you cannot have a capable big mass production, and the Raspberry Pi designer program can help your mass production. Then, so how do people do it? So now I have a Raspberry Pi and batches based on Raspberry Pi Pico, and you can so edit and so you make main holder for now B2C and DIY. So you can use on the Raspberry Pi Pico W and you have DIY. So now my community member tries to take the weather report with the Raspberry Pi and batches. And some people think about the question, first I don't have time to tell you. Please ask me after presentation how to get Raspberry Pi home. Now you can hardly to get it anywhere. So please ask me afterwards. And so now Raspberry Pi is hardly you get it, but on the Raspberry Pi 400 you can easily to get it. So if you don't care the keyboard itself, and please use the Raspberry Pi 400 as alternative. And their website, Raspberry Pi locators, and so information about that. So for more detail, so and check my Twitter, the Mastodon website. So please ask me to be the website. Via the SNS6 on the Mastodon or Twitter. Next talk, and hope to see you all at EcoScup 23. And because I'm managing Japan Trucks, and more I'm helping this with team. So thank you very much. And
Thank you very much, Mr. San. Questions?
How big is the Raspberry Pi within Japan?
How big is the Raspberry Pi?
Now activity is for 500 people, but the core member is 16 people, consisting of 8 months, 8 women. And mainly the translation team, and mainly so education team, and mainly technical evaluation. We now collaborate with the Raspberry Pi training and to field testing. So we evaluated the new latest product to evaluate to report to the Raspberry Pi trainings.
It's mainly in Tokyo, or is it?
Based on Tokyo. Yeah. And we will resume on the Raspberry Pi event and in summer to an offline event.
All right. Any other questions? If not, thank you. We good? Too large. While we get the resolutions sorted out, any dad jokes? Well,
the open source silicon ecosystem with Jupyter Notebooks. So I will do like a quick intro first, like I already did yesterday, just for people who are not there yesterday to kind of tell you what we are doing. So first, like my name is Toby. I joined Google like 12 years ago. I'm a developer for relation engineer, which means I focused on improving the developer experience on developer product. And I work on a variety of products, but recently I joined like the hardware toolchain team, and I'm focusing on open source toolchain for making custom silicon. So the mission of my team is to make custom silicon easier to build for everyone at scale, just like software. And like the vision is that imagine that you can have an optimization flag that you can pass to GCC that like gives you a silicon design to optimize what you are trying to do in software, but in hardware. Like sometimes when you optimize things in software, there is just so much that you can optimize software, and you often like at some point you will realize you will reach a point where you need to do an hardware accelerator. And currently there is a big gap. Like it's not even the same person who can do the two things. And like our goal is to enable like co-design so that the same people that work on optimizing software could also work on helping design hardware. And so for that, there was a lot of missing pieces 2 years ago, but the ecosystem has made a lot of progress. So now we have open source PDK, meaning the lower level of the stack for manufacturing silicon is open source. Like we managed to develop and improve like the open source toolchain for making silicon, meaning that you have a toolchain for you to convert your design into a file that you can submit to the Firmware. And there are more and more like design that people share and library that people share to an IP block that people share that you can reuse. And there are cheaper manufacturing options if you want to do custom silicon. So we really see like in those 2 years like the growth of the open source silicon ecosystem. And so I mentioned the open source PDK. So there is actually like 2 PDK that Google has worked directly with the Foundry for them to open source it. It's a PDK, the 130 nanometer from Skywater, and the 180 nanometer from Global Foundry. So we work with them to finding the right license and helping them open source something that works with the open source tool. But recently we've seen also a new trend from other Foundry that without even having Google talking to them, that go and like open source PDK. And that's like what happened with HP. So it's a Foundry from Austria, and they released their PDK. Like kind of, if you look at their repo, they try to follow the same organization that we did with Skywater and Global Foundry. And I think it's great to see that because it means that there will be more and more options for people to do custom silicon. And also, like the toolchain will be there because currently, like the toolchain were very skewed toward Skywater and Global Foundry, and like the process that HP builds is very different. So the tool will also need to adapt, and the ecosystem will get better. So this is one example of a toolchain that at least we put together by combining projects that were already there. There is like multiple ways, multiple tools that you can substitute there, not just like one toolchain that works for converting like your design to a file that you can submit to the Foundry. So when you come from a software background, you're not necessarily well versed into Verilog, into language like Verilog or VHDL. So sometimes people use what they call the 9-level synthesis, and Google is actually developing like a 9-level synthesis toolkit called HLS. And so there is a little language in there called DSLX that allows you to describe hardware with a syntax that's close to Rust. And so it's really approachable for someone who comes like me from software, because they can try to convert like the algorithm that they want to accelerate into that language and generate some Verilog algorithms. So once you have your X file and you can convert it to Verilog, you can run it through a tool for doing synthesis that's called YOSYS. So it's a tool that I've been mentioned this morning that's also very well used inside the FPGA world to do synthesis to map to an FPGA. Here you do the same operation, but you map it to the actual PDK that you want to use. So I will use YOSYS to make sure that to like convert my design into a series of get netlists that target like the process that I want to target. So in that case today, I'm gonna show a demo on how we target the Sky 130 process. Then there is a place and route tool on which you have that list of components that represent your design. You want to map them on the silicon die into so that it fits within that die, and so that like, the gates are close enough to each other to meet the timing that you want to do. And for that, there is a tool called OpenRoute that does this place and route operation. And then the last test is that you want to generate a file that you can actually send to the Foundry. And that file format is called GDS. So this will take like the design data from OpenRoute and actually generate a series of basically polygon and rectangle that you can like submit to the Foundry. And for that, there is 2 tools that we use called Magic and Caveat. So at first, 2 years ago, it was very difficult to install all of those tools. But we've made a lot of progress into packaging those tools into things that are readily available into an environment like Conda. So if today you run that inside the Conda environment, you can get a PDK, open tool that contain that depend on all the tools for doing synthesis spacing or and GDS streaming, and also XLS, which can go IO-based synthesis. And there is also one other barrier was for people to be able to share their design with each other. You might be, you know how to run the tool, you know how to run them inside the correct order. You might have a pretty picture of your chip that maybe you want to share with someone else. And there was nothing really that was tying all of that together. So we started using Jupyter notebooks to do that because it's very convenient. You have a series of text that you can put with command that people need to execute. And instead of just being a README that people copy code snippets inside that terminal, that's actually something that you can execute. And you can produce interesting visualization about your chip and how it works. And so that's what I want to demo today. There is this project under the Chip Alliance repo where we store a lot of notebooks that are using this toolchain. And I want to show how it looks like. So if you want to follow along, feel free to open that URL and play with the notebook yourself. I will go quickly through one that shows how that works. Another aspect is that it's you don't have to install anything on your computer if you want to do that if you're using a notebook hosted service like Collab. So Google also have a notebook hosted service called Collaboratory where it will start a machine in the cloud to basically run the code that's inside the notebook.
Is there Collab link also? What? Do you have Collab link? Do you have this notebook also?
Yeah, so that was on the URL that I mentioned here. So if you go to that URL here, the URL that I just so yeah, if you go into that URL here, you will find a series of notebooks that you can open from the README. The actual one that I'm going to use today is that one, the XLS workshop.
Great.
So it's like that. And so that's a notebook that we used. It's too small. So that's a notebook that we use for running workshop in Tokyo, with the University of Tokyo, to get actually CS students that know nothing about hardware design, but familiar with the concept of chip design and familiar with the tool that you can use to do it. So the first thing that it does, and that you need to do, is to click this cell to install the package that I mentioned. And after that, there is a small introduction text about HLS. So HLS is basically this high-level synthesis topic I mentioned before, where you can describe your the operation that you want to accelerate in either C++ or DSLX, which is this direct Rust. It really works like a compiler. It will have an intermediate representation. It will allow you to run some interpreter and some tests. So you will, as a software engineer, you will feel right at home because you will be able to validate your design by writing unit tests. And then you can run a series of optimization and finally spit out the very log that you can plug with the rest of the toolchain. So the design that we are going to do today is very simple. It's going to be a chip that adds 2 bits. So it's going to. So here you see that using that language I can write a function. It takes 2 arguments, 1 and b, that are all both 1 bit wide. So u1. And it returns another value, which is a u2. So because if you can overflow and have a carry, so I need 2 bits to start. And I really describe my operation like I would describe in software, saying that the result is equal to a plus b. And because I want this function is the core of my design, but I want to wrap that into an actual chip. And so today I've decided that I'm going to use a chip that has 8 inputs and 8 outputs. So it has 8 pin in and 8 pin out. So I need to decide which pin I want to send to this adder, and which pin I want to send as a output. And because it's code, I can write unit tests. So I can verify that this adder is actually working. So if I press here, I can see that the tests are working. So now that I have like this description, I can run like the toolchain to convert it to this intermediate language called XLSIR. So here I see like a view of the lower level operation that I will have to perform to actually perform this other operation. And then I can generate the Verilog for it using the same toolchain. And here it's a bit silly because that design is so simple that it's actually very similar in Verilog the way you would write that thing. You would just write like I want to activate a new user plus operation. And then like once we have that Verilog, we can connect it to the rest of the open source silicon toolchain. So I can take my Verilog, run it through the synthesis tool, run it through for planning, go it all the way to GS streaming, and get a file that I can send to the firm. So for that, I need to specify like what is the name of my project, what is the Verilog file I want to use. If I need a clock, I need to specify the frequency of my clock. And I also need to specify more physical constraints, like how big will be my chip. So here it's going to be 50 micron, and how packed I want the gate on my chip together. So here I say I want 30% density. I also need to decide things like where do I want my pin. So here I'm saying I want like the I/O, the input pin on the left, and the output pin on the right. And you notice that the I/O in here and the out actually corresponds to what I used inside my code. Right. And once you do this, you can run like the first operation, which is synthesis, which will basically convert like our like Verilog or Verilog description of the design that we want to do. Like so, this like 1 plus B into actual gate that are using the PDK that we want to target, which is the Skywalker process. So once we run that flow, now we get like a representation of basically a netlist to describe the gate that implement this operation and how they are connected together. And so here you see that for adding two numbers, I need two gates. I need a XOR gate for computing the lower level bits. And I need an AND gate to compare the most significant. And so I can see that those gates are where they are getting the wire from the input. I can see how they are combining the wire, the bits at the end, and I can see how they are showing it to the output. The next step is to do floor planning. So now I need to take those gates and put them somewhere. I need to kind of prepare the place for putting those gates on my chip. So after I run the floor planning, I should have like this an actual chip that has the dimension that I want, so this 50 micron. You can see here I have the input pin, so the 8 input pin, the 8 output pin. I have the power delivery network that will allow me to power my gate. The two gates are still here in the bottom. They are not placed because I didn't do place in out yet. So here you can see there is an AND gate here and the OR gate over there. Next step that we need to do is placement. So now we're going to take like those two gates and we are going to try to place them somewhere where there is space on our chip. It's not very hard because no our chip is empty. But, so they will end up somewhere in the middle. Yeah. So here we can see there is a two gate here on that. We can even like remove like the I/O element. So you can see them here. And so the last step of the next step that we need to do is routing. So we need to actually connect the pin of this gate together so that they actually electrically like are connected like the netlist that we had at the beginning. And so at the end of routing, we get something like that. We toggle this and this. So here you can see we have our two gates. You can see like there is a wire that comes from the input that goes into the first XOR gate. There is a wire that goes from the second input there that goes inside my OR gate, my XOR gate. Then this XOR gate is connected to the AND gate there, and the output of the AND gate is connected to these two gates here. So now like I have a physical representation using like the process that I want to target that implements the circuit that does. And the next step is to stream the GGS, and then you get like a fully functioning, fully complete layout that you can submit to the foundry for fabrication. And a series of metrics, and you get to check if like this design, the way the polygons are mapped together, actually conform like to the constraint that the fab has for manufacturing that chip. So there is a series of rules that we need to follow following that. And so like that was a bit of a toy design, right? Like it's just something that I like to know. But we can also like do more complicated designs. So like here, for example, we can easily turn like this adder into something that multiplies to number. So if we run that, we can get the very log there. And if we do the synthesis, we're going to see that multiplication is not as trivial as it looks like. And that I need a lot of gates to actually implement this, this multiplication. It's not even big enough to fit on the screen. We're going to see that when we run the actual flow. You can see here, I'm going to run the flow and try to put that inside the chip that I defined. And we see it fail. And the reason it failed is that there is not enough space to put all those gates on the chip. So for it not to fail, I'm going to make the chip a little bit bigger. It should take maybe 1 more minute. And now I can see the report. So you were asking how many gates there were. So there is like 69 gates. And here we have a breakout of what they are actually used to do like our multiplication. So when we write the code, we just write one character, right? And we don't really realize that actually to be implemented in hardware, it needs a lot of circuitry. So we have 10 gates, like 7 nons, like 2 NOR, 7 XOR, 13, 7 OR, 13 XOR, and there is a lot of gates there.
That's 8 bit by 8 bit, right?
4 bit by 4.
4 bit by 4.
And yeah, if we take a look at the chip, it's going to look like this. So you see, like the tool have to do a lot of more work there to lay out all those gates, and we actually didn't have enough silicon space to do that. So, like, if you want to follow and redo this tutorial at home, it's all like inside that repo that I mentioned, and there is a few more exercises toward the end where we actually go through the step of pipelining that design. So making sure that we can execute this multiplication into multiple cycles to reduce, to try to reduce like the latency, improve like the throughput of our design. And so let me try to continue and tell you like what I think that book are also useful for. So we've seen here they are useful for designing. I can run a tutorial workshop. I can share a design with you that reproduce my chip, and you can run it on your computer and get a pretty picture. But it's also useful for research. And so, like inside of the LSI field, there is actually a problem for reproducible research. Like when someone publishes a paper at a conference announcing like a breakthrough into a computer architecture, like usually what they submit to the conference is a PDF. And there is a little table in there that says, oh, on this process using this proprietary tool, I got this result. And the table is the only thing that really validates the results, and it compares like the research to other projects that may be older projects that are doing submitted concurrently at this conference. And there is actually no way that you can compare those things together because I'm not using the same process. You cannot run the same thing to reproduce it yourself. And so, like, your book can also be a useful thing for that. Like, instead of submitting a PDF that's static that just presents your result, you can actually submit a recipe that people can reproduce on your own. It might target an older process, so it won't have like the same performance as like a state-of-the-art thing, but it could help people like build on top of your research and also allow people to collaborate together. And so, like the IEEE Secret Society actually started like something that I think is a great initiative. So they are based on the same toolchain, based on the same PDKs, and they basically invite any student from any university to submit notebook to get invited to their conference to present their work. So usually those are like conferences that are an undergrad because it's like too prestigious to get in, and that's an easy way for them to get inside of this and to get familiar with the open source toolchain. And they've got like 14 projects just submitted last week for the upcoming BASAP conference that's happening in Japan. I think that was like great. Thank you. And like the other thing that notebooks are great for doing experiment and doing visualization. And actually, like if you parameterize your notebook, you can run like the same recipe that I was doing here with a fixed size. I can try to run the same notebook with many different sizes and analyze, for example, things like the power consumption. And here it's an experiment I did on Google Cloud where I run like 10,000 jobs, like I've just shown you, with different size and different density. For a much more complicated design, like a RISC-V core, and I analyzed like the power consumption of each of those designs during simulation. And here you can see each of those dots is like one of the jobs that we've run together there, and like the power of the dot is like the lesser it consumes. You can see here there is like you can have a nice like sweet spot there between the density and the area where I consume the less energy. And maybe that's something that's very well known inside the field. If you have like 10 or maybe 30 years of experience, you know that if you have the good trade-off between area and density, like you end up consuming less. But for me, that's like new to the field, or for anyone, like they can start using the structural resource and start acquiring that culture without spending 20 years, just by consuming like a lot of resources. And like in order to fabricate like this design, we run like a program like during 2 years that allow people to submit designs that have been created using this open source tool and to get them manufactured at no cost, as long as the design is open. So Google has been running those shuttles like for 2 years, and we've run 9 of them, and we've seen an increased number of engagement there. Like you can see at the very beginning, we were getting only 30 projects. Now we are getting as much as 140 projects to the last shuttle. And like people are submitting from all over the world, so it's a very diverse community. And like currently we are busy like trying to bring up like the design for the second one. And so people got back their silicon. I have an example here of one of the chips. And like they're trying to run like validation to make sure that the chip is working. So we bumped into some issue with the toolchain. We bumped some issue for some of the parts that were coming by default inside the silicon. There was like some timing violation that people needed to work around to, but the community can get together, manage to produce the right characterization logic to protect the chip, and we've seen like good results of people getting working silicon. One example that I wanted to show you is like actually this chip up there, which I think is very interesting. So here you see those are the 40 chips that got submitted to the shuttle. So each of those is like an open source design. Inside of this one, you can see that there is like many other elsewhere. It's actually a design from an online course. So someone ran an online course for designing chip, and they ended up taking one of the specs there and like putting 16 designs inside of it. And so as part of the curriculum of that course, you have to produce a design, and then at the end of that course, you will manufacture the design on that shuttle. And that person had like no interaction with Google. They did like totally that on top of the infrastructure that we were providing. And I actually got like a copy of that chip that's like here. And so it's the one that's inside the upper corner here. It's a very trivial design. So it's a Fibonacci generator. And so it just takes 30 pins of the design and we put like Fibonacci number on every cloud cycle. But I wanted to verify that this chip is actually working. And so I could run like the bring up sequence that like the designer has on my computer. It was difficult for me to share the result with someone else. So I ended up creating like another notebook that allowed me to do that. So it kind of like go through the setup for finding like the configuration of the I/O that actually work. And I can show you quickly. Each write like some firmware to initialize the I/O. So actually there is 5 chips on every one of those chips that we manufacture. That's here for bringing up the I/O and connecting to the logic that the designer is putting together. So I configure the I/O pin there, and I start like the design. And after I'm done with that, I'm actually connecting to a board that's underneath here. So here you see like you have like the chip, like you have the hat, and underneath you have a little like nuclear board. And on this there is actually MicroPython that's running. So I could write some Python logic that will try to read the pin of the design and verify that the behavior is right. So here, like I'm connected to one of the pins that represents the clock of that chip. And you can see on every iteration, I'm clocking the device. So I'm just turning the clock from 0 to 1. And so that will like step through the logic of that chip. It will get the clock and execute that Verilog, and we put the next Fibonacci number. And on each clock cycle, I'm reading all the GPIO and putting them back inside the number. And so you can see here, these are all the numbers that I was able to read. And then I can execute some Python now on my computer to actually like take these files that I got on the device and put them into a Panda data frame that I can actually manipulate. So like Python is great at doing that. And then I can, on the local computer, like do the real Fibonacci thing and like try to see if the results are the same. They can look similar. And then I can try to visualize them and see, like, for each of the bits of my design, each of the I/O of my pin, do I have the same thing that the Fibonacci has? And so that's one example of how you can like create a bring-up sequence that anybody could reproduce. And you know, when you manufacture silicon, like not all the chips are equal. Some of them chips are somewhere right inside the wafer and might behave not similarly. And I got actually another chip that I got there. I rerun the same thing, and you see, didn't go so well. There is like some of the pins that are not matching. So that's like definitely something that's convenient. So I can get like those chips one by one and actually test them. And like I got this little sheet there where I'm taking the chip one by one and kind of return them if they work or not. And so yeah, that's what I want to show. I invite you like to join like the community. We have a Slack community with like more than 4,000 members there. There is this portal that we put together, developer.google.com/silicon. There is actually an opportunity to take out this month with the project called Tatni Takeout. So they take like one slot of a similar shuttle, but instead of putting one project in, they put 200 projects. And so they're able to bring down the cost of this shuttle like pretty drastically. So you can get the design in there for $25, and if you want to actually get a chip for that includes actually the 200 project. You can just pay 100. You have to pay $100, but you get like a chip plus a PCB. And so yeah, that's not something that's tied to Google, but it's just like a cool initiative inside the community I wanted to point out. And later today there is a talk from Shane Cross, who is actually a user of Sushen and did like a lot of experimentation to trying to build a SOC using this open source tool. And so yeah, thank you.
Thank you, Johan. Questions? I'm sure there is. Yes.
My question was about the higher level abstraction above virtual XSL or XLS. I assume that same abstraction can be used as a precursor to an FPGA.
Oh, it can be used for FPGA as well. And one interesting characteristic of it is that it has these intermediate languages that could be JIT. And so you could execute on your computer like native code that implement the same thing as your design. So for like very fast simulation, that's actually very convenient.
Any more questions? Wait once, yes.
Yes. So you talk about like a certain way to like how to say program the chips, right?
Yeah.
Is it similar to like how NVIDIA does it with their CUDA or something?
CUDA?
No, like NVIDIA have like directly programming their
There is like multiple layers. So the lowest level is that you can actually design your own CPU and put it on that chip. And then there is like you can upload like your own firmware that get executed on that custom architecture that you design.
So there is like the code that is compiled specifically for that chip, right?
So like there is, let me go back to actually this. I think that one is so yeah, so you can see here that's like one of the chips that helps me on the shuttle. Like underneath here is like a management SOC that comes on every single project. There is a little RISC-V on every single project that will allow you to kind of verify that your design is working. So that's like something where you can put your own firmware, and that's you program it in C, you flash that firmware, and it gets executed when the chip will up. And then there is like your custom logic here, which is connected like through a series of pins to that RISC-V chip. And so from your RISC-V firmware, you can actually send some I/O, all the I/O of your custom design, and verify that it's working. And there are cases, for example, like this project, where they ended up implementing like a RISC-V CPU inside the user area. So you have like the little RISC-V CPU here that we provide, that's here for doing the diagnostic, but the user design itself is also a RISC-V CPU that can have its own firmware and communicate with that other RISC-V CPU to verify its working. And like that one is even more fun because like using the Skywater process, they were able to implement an FPGA. And so like they actually designed like the fabric for the FPGA where you can like flash a bit stream that's done using the open source tool. And then like from the little RISC-V that's over there, you can like call the FPGA and verify that it actually do what the bit stream is doing. And so, and they run some pretty impressive demo on that FPGA here. So that was really impressive. So there is really like multiple layer where you could program that thing. You could have that designing, the design that you put in silicon there, it's an act of programming because you can describe it with a syntax that's close to code, but there is also like the thing that you run on the thing that you designed, which is also another way of programming it.
All right. Any more questions? Otherwise, we have to wrap up. Okay. Thank you very much, Johan.
Yeah, and show the chip afterwards. Okay.
Okay. Okay. Yep. Okay. Good afternoon. I'm Rob Turner. I'm talking about a project to automate the testing of home radios for amateur radio. In case, how many of you know what amateur radio or home radio is? Excellent. So in that case, I won't explain it. I'm going to say that this is a cool event as well from Singapore, operating with a 10-meter aluminium tube, radio with a normal battery, and I guess we'll work with some of the models, so that's obviously not working. Seems like such a So that allows us to operate stations as far away as Portland, Oregon, which is roughly that direction. Okay, so another part of the hobby is to make your own radios. The term homebrew is used by analogy to homebrew beer. That is to say, a licensed operator can certainly make a radio for their own use, but can't sell it. At the moment you bring a radio to market, you end up with a bunch of technical rules. The method for testing radios historically has been to buy an expensive instrument which is a spectrum analyzer essentially, with the usual antenna ports plus control ports and audio ports. However, A, they're expensive, and B, they're not necessarily optimized for what amateurs care about. So, in principle, if you're doing a homebrew radio, you get some parts, you solder them together, you operate them, everything is awesome. Okay, you know I'm lying. So there are a number of problems that are even worse for radio. The first is that some regulators are getting nervous about this, and increasingly so. IMDA, in particular, here in Singapore at the moment, is unable to say yes to this. They haven't quite said no. Yes. But I got that. Yes. 4 months, you haven't got an answer. That's quite, yeah. So the next and the really big issue, and the legitimate issue that concerns, that concerns IMDA is interference. It's really easy to create interference, and it's particularly hard to detect. A major area is harmonics, spurious tones that are multiple at your carrier. An example from a ham fest in Daytona, when someone brought a bunch of lab gear and did free testing for any radio anyone tested. A guy turns up with his proudly modified HT walkie-talkie to increase the carrier power. And so they hooked it up and measured it, and not only had he reduced the carrier power, he created a third harmonic that was larger. Now, this was a 2-meter VHF, so the 70 centimeter harmonic was in an amateur band, but it's an amateur secondary band where listen before talk rules apply. And of course, if you don't know you're transmitting on the band, you can't listen. So he was in fact breaking the law intentionally, albeit in a not very serious way. So it's a very large part of the risk is that you're doing harm that you don't know you're doing. And so it's that problem that I'm looking to help simplify. It's not the whole issue, but that's certainly the biggest one. And from the standpoint of the regulators' risk management, that's really the issue that I'm hoping to offer some comfort. The next is a broader issue with making your radios, less so perhaps at HF, but it becomes a larger issue as we go out. There's a lot of things to test. Yes, nowadays you can get a $50 tiny SA and verify that your radio is not emitting stuff that it's not supposed to be, or just own more expensive instruments if you can afford to. But actually, it's a bunch of other stuff that you like to care about. Is your oscillator drifting? Are you using as much modulation and deviation as you're allowed to, because that makes your signal more readable? Are you operating inside a lawful bandwidth? Is your phase noise visible? This matters for weak signal work, where the phase noise in the local oscillator can in fact overwhelm the signal that you're trying to detect. How sensitive is your radio? Is the level of receptor appropriate? This is good for receiving close to legitimate, very powerful signals, very close to a weak signal you're after. Again, this is another piece of the puzzle. All of this stuff is time consuming, but okay, maybe we can automate it. And it all requires costly equipment, at least in principle. It occurred to me a while ago. I spent quite a lot of time watching a YouTube channel called The Signal Path, which does a lot of time going through the architecture of test equipment. Almost all of them are a low-end PC, a little screen, not very powerful CPU, a crappy keyboard, a bunch of special buttons that are used to work your way through menus. What we might think of as an SDR, a DAC, an ADC, and FPGA or ASIC or set of ASICs to process the data at its highest sample rate. And then various sort of workbench items, attenuators, filters, oscillators. Maybe I could make one of these. So the context is what I want is a box. I do not want to put yet another little screen and a bunch of buttons. People have a mania for that, hate it, it's revolting. I like using my laptop, I have a bigger screen at home. I'd rather just use a web interface, talk to it over an Ethernet port, and voila. And not provide any user interface on the front of the box at all. Just a power switch, a power line, and a bunch of sockets. And then have your antenna, microphone, speaker, push it to control lines to the device interface. And so then you sort of talk to it using your laptop. Inside the box, the design is relatively simple. Something like a Raspberry Pi, a USB sound card, a USB SDR. I'm looking at the Line 7002, the Line SDR. Another candidate, perhaps, is to take my Novena, which has the Line 6000 chip in it. Sadly, not useful for HF. That has a low frequency of 300 megahertz. So how many people know what the Novena is? Only a couple. Okay. So Bunny is on the room and built an open NVIDIA laptop a few years ago, which included an SDR chip. But okay, that's an aside. The rest of the design is fairly straightforward. Optocouplers to isolate the GPIO pins, things like pushing the transmit button, because you otherwise end up with parasitic currents making their way back into your test device and your laptop, and that causes, if you're lucky, it just causes things to go wrong and run up. It destroys things, especially if you've got tens or hundreds of watts coming out of your radio. So that again is an issue with amateur radio that doesn't arise in smaller IoT applications. Speaker mic, a simple isolation. The one area that perhaps needs a little bit of explanation is the radio end itself. You need at least two different attenuators doing two different things. One has to cope with whatever the output power is from your transmitter. So if you have a few watts, then okay, you have a small attenuator. If you have a radio that puts out a few hundred watts, you need an attenuator that's physically quite large to get it down to something you can then put through your precision step attenuator and then into the input of your SDR. The other big issue is calibration. This applies to all instrumentation, but certainly if you're sort of cobbling together cheap hobbyist bits and presuming to measure the performance of a radio in a way that might be pleasing to a regulator, calibration becomes a really important question. I'll come back to that. I found quite a unique way of dealing with it. So, certainly for any transmitter tests, and so most of my time so far as well, the big question is power. How do you measure power? So here's a beautifully simple way of doing it. This is Community Radio, Community Radio Companion, which is the Community Radio. We take a source, we do some high
Power. You have a power issue.
No, I have.
There was measuring power.
It hurt me. It's like, okay, I'm going to turn the power off. No. Sorry, that's not good. Okay, so we do some low pass and high pass, we're going to get the rubbish. We neatly, this is one of the companies built into the radio, do a complex to max where conversions. And samples this far are INQ. You're sampling at some frequency, and then you have sampling again a quarter cycle delayed. So the same frequency, but delayed 1/4 cycle. And so what you have conceptually are two samples that run into each other. To compute the magnitude, you just multiply them and take the square root. Community Radio follows this complex to mag squared. We switch here from blue being complex and orange being real. What's important about it is that so far you're looking at voltage. Here, however, if you just multiply them together, you're now looking at something that varies with power. Power varies with voltage squared over impedance. Now, so you've got a series of speed samples here that are linear and proportional voltage, which is great. You need to multiply it by a constant. What constant? That's the calibration problem. Getting from this all, we spend an hour on why what's coming out here is not and can't be directly read the kind of radio, but over a short range, you can say that 10% change in the radio's output power is a corresponding 10% change here. And so as long as you've got a way to calibrate, you've got enough basis for saying, here's a number, dear regulator, that's probably within about 100% range. And for the purposes that we're trying to solve, that's enough. So again, this is like, how do we do this cheaply? Do a moving average. You have to do the averages on the linear measurements. You can't average anything else. Then take a look and convert to decimals. Okay, this is awesome. This gives us how much power is coming out of the antenna socket with a bunch of qualifiers. That's not enough. It's important information, but it's not enough. The reason is you need to know about how much of that power is present in the harmonic and how much, sorry, in the fundamental, and how much is present in harmonics. If your radio looks like this, don't ever connect it to an antenna. This is approximately a square wave. It's 1 kilohertz, isn't it? I'll give you an example, but it's like but the fundamental is about 3 dB below what's expected. The third harmonic is only 10 dB below it. Even in the simplest of regulatory cases, this is the worst permissible performance here is that it's 43 dB or 20,000-fold below the carrier bound. So this is 1,000. If this were an actual radio, this is 1,000 times the simplest possible compliance case. And actually, if you move under various circumstances, that the compliance requirements get tighter. So you don't never look on it. But what I'm saying is, it's not enough to know how much power can out of the socket. You do need straight away to analyze it by frequency. The harmonics are relatively easy because the filters are not terribly difficult. If whatever your fundamental is, you can readily build a filter that goes 10% either side. And then you can sort of move that up to the first harmonic to that, and then the second harmonic to that, sorry, second harmonic, third, and so on. And so you can get your spectral breakdown pretty cheaply in software without any complicated maneuvering. That's a really important test, and it's a regulatory one, not a usability one. And fortunately, that's relatively straightforward. Another big one is phase noise. And this is a particular interest of amateurs because of the habit of listening to stuff that's come by the ionosphere and therefore is incredibly weak. So, start with a presumed near pure tone at whatever the reference is, and then a nearby signal, 100 megahertz is 20 kilohertz to me, that is at 90 dB down, a big nth. It seems like a very small signal, as far as amateurs are concerned, that's huge. You've got off-the-shelf radios that go 60 dB below that. However, if the oscillator in the radio is using PLL, which is DVR, to keep the average frequency right on the line where it's supposed to be, the operation of the PLL to continually step the control voltage up and down, or the counter ratios up and down, causes noise that looks like this. That's referred to as phase noise. And you can very quickly have more phase noise than the signal you're trying to receive. And so regulators state numbers, they don't much care, but you certainly, as a builder, it's of interest to know that you've made a mistake that's drastically worsened the phase noise present in your design. So there's a whole lot of difficulties here. Unfortunately, to make a confession, the reason I'm not showing the device is I spent much too much time understanding this problem and don't yet have running code. So this is where I'm going, not what I've got. I'll come back to that. Oh, no, sorry, here it is. Right, okay, so the issue with phase noise is you've got to measure close in. In a spectrum analyzer, you do this with an IF filter that's really narrow. Typically done electronically or part electronically, part computationally. They're expensive, and they're fiddly if they're electronic. If you do it computationally, you use fast Fourier transforms, you add a whole range of new sources of error, each one of which has to be corrected for, which is not only fiddly, but computationally expensive. And my plan is to run this on a version by zero. I suspect I'm going to run into a problem. The interesting news is, of course, for the line SDR, there's an FPGA available, so not sure. There might be some guys. The other big issue is the calibration. This I was concerned about until someone drew my attention to WNGage this stupidly clever way of solving the problem. Start with a reasonably clean oscillator on arbitrary frequency. These are available off the shelf for sets. All you need is it's a reasonably clean sine wave. So no PLL, just a crystal. Jam a pair of back-to-back diodes across it. This revolting procedure has two effects. One is you now have a substantial energy component double the frequency. The other is that the peak is predictable. It's not going anywhere. Silicon diodes don't tend to change their current voltages at any time over a period of decades. So give or take that the other components not change, the silicon diodes aren't going anywhere. There might be a thermal problem. I haven't looked carefully at the thermal characteristics of a 4148, but there are other components that are sort of cheaper and fairly stable, relatively cheap and relatively stable. So what you then need to do is remove the second harmonic, which is what this thing is doing. This becomes conductive at a frequency. You basically tune this to be the second harmonic. Therefore, you've got back to your sine wave, but it now has the rather a fixed power level. Whether it's the intended power level is not important. What's important is it's predictable. At that point, you walk into your friendly tertiary institution or lab and say, "Hi," and I've had one here volunteer for this. Could you please do a calibration run on this? That then becomes the basis for the subsequent measurements, because this then solves a whole lot of uncertainties, or this works around a whole lot of uncertainties in my otherwise extremely cheap and unsuitable design. The other thing I missed in my early design is the other obvious fact that I'm not calibrating across the. So in fact, likely there are more switches that are calibrated available in antenna socket as well. This also comes up when you get calibrated by some party. So consider this a high-level design subject to some significant revision as it becomes concrete. So what's left? Write the code. Again, I apologize. The phase noise thing does concern me. It's relevant to be able to receive HF signals that have been propagated by the ionosphere. And this seems to be you can spend as much money as you like. The American Radio Relay League actually publishes its test procedures. They state a specific oscillator from Wenzel. I approached the manufacturer and asked, it was a $3,000 item. However, you can do useful phase noise measurements by having in your test instrument an oscillator that's only slightly better than the oscillator that's in your radio. So take whatever's happening in the radio and you go double the price, and that is a reasonable oscillator to stick in the test instrument. You've got enough basis for discovering that you've made this. What you're looking for is a serious mistake, not an adequate. Okay. I'll just stand very, very still. Or not.
Very good.
So the so this is it's going to be a trade-off at any point, and I haven't yet gone ahead and had to. What I have discovered is that not only is the oscillator expensive, but computationally it's difficult. I'm not going to do it now. It's also electronics, so it will be done computationally. That gets into a whole sort of. If you're doing FFT, you've got to have buckets. And if the tone you're measuring is split between two buckets, then the two measurements come in 3 dB down. Okay, the fix is together. But easily said, hard to do. There's an issue with PCM noise for some of the measurements. I think it's okay, but I haven't yet convinced myself that it is or isn't. The analyzing in a time discrete way, of course, doesn't perfectly reduce the source wave at all. And the risk is that the time slices introduce enough noise to exceed at least the 3OI and possibly IMD performance of the device in the test. Not sure, probably not a problem, but I haven't yet convinced myself either way. The really big one is that this relies on a control channel. And so we go back to that Norcal 4900 and the Altoid team. Its controls are a variable resistor for power and a variable capacitor for tuning, neither of which this device can control through a serial port. And so there is this gigantic qualifier that says that for this to be meaningful, the radiator testing has to have at least a microcontroller with a serial port. And it's then using reactors or capacitor banks or whatever to do the control rather than actual volts at the user turns. And for a lot of homebrew, that's actually a problem. That we're sort of building traditional designs that fit Altoid teams, make it too complicated if you have to add a microcontroller, particularly off the shelf unit. Another issue is this is similar to the issue with cinema actually, synchronizing the sound card and the SD. So in cinema you do it with clapperboard. You're synchronizing the video of the sound, you have a clapperboard which makes a sharp pulse on the sound and a visible form on the video, that's enough to light it up. I don't have a good way yet to do the same thing with a cheap sound card and a cheap SDR. Working on it, but it kept them on its unsolved problem. And finally, this one, regulators all over the world are doing this. Singapore added it to the amateur radio spec about 3 years ago, and that's the EMC stuff. They're more concerned about emissions than about acceptance, of course, but they do want to hear about both. A very early parts of an approach to do that. They're looking for ideas for benchtop EMC. You find metal boxes, sometimes called 10 cells, sometimes called real chamber made out of micro oven. There's a few different ways, because they're radio talk. There's a few different ways of doing it. That's far more ambitious, but IMDA is already asking, and in the context of homebrew, like the spec they point at, you can operate an EU spec or a US spec. The EU spec actually states expressly that it does not apply to licensed amateurs making radios for their own use, or actually named as the only user class that's named in the standard. It says this doesn't apply to these guys because their stuff's not coming to market, therefore don't use it. And I'm just saying use that standard for homebrew. So maybe, hopefully, we just avoid that altogether because it's ridiculous. If you're making a medium level device, a small problem with interference is a significant issue. If you're making one, not so much. Anyway, that's where I am. Questions, comments?
How do you know that you're not breaking the law while you're testing?
How do you know that you're not breaking the law while testing? Yeah, this is a even more difficult question. So, at least with respect to IMDA, what they're looking for is that the device itself that appears in the license, they formally authorize that you hook up to an antenna, behave sensibly. Yes, it's a near certainty that there's an amount of emission occurring during testing, like tracking spectrum nozzle on a bench. Yes, for sure, there's some amount of leakage. You've got a handheld on the test frequency, it will go into full firing unsquelched. That's not the concern. The concern is almost a bureaucratic one that says we've authorized you to connect this radio to an antenna and transmit power. We want to be convinced that the thing that we've given you permission to do is reasonable. More generally, low powers. You don't, in general, put single-digit watts, let alone tens or hundreds, into a test environment until you're certain that the milliwatt and microwatt range that everything is working correctly. And only then you start working out power amps and all that sort of stuff. But yeah, sure, the whole thing is a compliance question. So like, how do we avoid getting ourselves into a deadlock? Sure. Any others?
Sorry, didn't really get the bit about EMC. So it's an emissions requirement?
Emissions and acceptance.
Okay.
So a device, if you're looking for benchtop EMC, one of the things TEM cell used for was torture testing. You put a device in a TEM cell, and then you put a kilowatt of power in it. And the device has to not malfunction. So for example, if it contains a transmitter and a microcontroller, the microcontroller must not, timing is actually okay. What it must not do is select an impermissible frequency and begin transmitting just because of the presence of some of it. So that's a bit consumer protection. It's a little bit hypothetical because for an amateur, it's like my radio's not working, I'll turn it off, okay, why? But this is IMDA taking a very consistent approach. And I sort of get that. But it means that, because the same thing asks us about safety. Well, that requires testing at 16,000 volts. I don't want to do that in my apartment. And B, you test it as part of the test, you test the instruction. If you do it in the lab, you send 2, and you get back 1. And so again, this is sort of overkill for amateurs because it's really consumer protection. And for homebrew, there's no consumer. So what I'm hoping to do is put it on IMDA where it says, look, here's a way to take away the bulk of the risk that happens. Is this enough? Time for more, but
yeah, when you design your amateur radio, right, you need to have a specific frequency for the filter. I mean, for the commercial radio, we only have a specific frequency, right? So let's say we go beyond that frequency. Is it okay to use, or need to get something like authorization from it?
So EM spectrum is an extremely valuable resource. If you are transmitting where you shouldn't be, expect to get into all kinds of trouble. The guts of it is, and in fact, we've hit this with the use of software-defined radios as radios, that one university group was finally able to get IMDA to say yes. And the only way that approved was if there was a analog electronic band pass filter, not just high pass, sorry, low pass, which is what you normally have to do for your transmitter. They wanted the full band pass to say, okay, you can operate this thing, but we want a filter that sort of independently of the software that's under control ensures that this device cannot radiate outside the licensed band. And so the way that tends to play out so amateur gear tends to be very frequently agile. I have a radio, like most use radio, in fact, that operates as a transmitter over 200 to 1 frequency range. And you just can't do that with one filter. And so if you pull the radio apart, the bottom half of it is a deck of filters, 15 or 20 filters for each of the different bands. So yeah, as a sort of rational engineering, and in some cases as a regulatory requirement, the answer is you put in place filters that will ensure that you're not accidentally transmitting outside the intended frequency. Cool. Thank you.
All these restrictions or aspects, is it also mainly because of Singapore? If you go back in Australia?
What happens in other jurisdictions? Yeah. So Australia is a little more laid back. I haven't looked at the Australian rules with respect to homebrew specifically, but certainly the interpretation that is applied is that, so the difference is, one of the differences in Australia, you don't register your equipment. Here we do. So the obligation in Australia is, as a licensed operator, it's incumbent upon you to stay within the law. Same as driving a car and not exceeding a speed limit. Only for where the risk is very high, like heavy goods vehicles, do authorities, the LTA does it, many others do it, insist that the vehicle has an automatic device to throttle the engine if the speed exceeds a certain speed. For everybody else, it's considerable to rely upon the fact that the driver is trained, has passed an exam, has applied for and received a license, and that license can be cancelled. And there are significant penalties. Same in radio, like 2-year maximum prison terms. So it's sort of the same setup, but we've ended up in a bit of a deadlock, sort of dead end with IMDA. In Australia, they're not registering equipment in the first place, and therefore the requirement is only that you operate. Whatever you're doing, whatever you build or modify, must operate within the terms of the license. But Australia is a pretty permissive environment. I can turn up there with a Singapore license and my gear and operate Australia without telling anybody. So it depends. It will vary from jurisdiction to jurisdiction. All right. Yep.
So thank you very much. Thank you. laptops and servers. And I think that's going to be an interesting. Do you have that for a RISC-V system? That's been the flavor of the
I will criticize RISC-V.
Oh, okay. All right. Thank you.
Some balance.
This
Yeah.
is a talk for realistic people. And we also only have 1 hour, otherwise my laptop will be empty. So, okay, we can start. I stay here for the camera. Okay, so hello everybody. I'm Kai, and this is my talk here for open source firmware for Intel NAND-based laptops and servers. And looking back at it now, this is an absolutely terrible title. And let's fix that and make it a bit more shorter and say, okay, what we want is a free open source laptop, right? And it has to be, we want it to be accessible, practical, and affordable. But before I tell you how to get this, we have to suffer through the information. So I'm very short about myself. So I'm co-founder at NEO. We do firmware-based security using authentication. I also wear many hats. I'm also a member and founder of the Open Source Firmware Foundation. And open source firmware is exactly what we do there. And we're trying to push open source firmware in the general systems we have, right? And Intel-based laptops and servers. So we're trying to push Cobol, for example, and allow you guys to get systems that have open firmware running. Okay, so firmware. How to find firmware? In the PC area, we always know this as the BIOS, right? So this is a picture of the original IBM 5150 mainboard. The thing contains a lot of chips. One of them is at position U33, is the BIOS chip. At that time, the BIOS was actually a set of routines the operating system, in this case, this would be Microsoft MS-DOS, would call to do stuff like print stuff to the screen and maybe talk to the disk controller and stuff like that. So it was kind of an operating system in itself. Nowadays, these things look a bit more like that, right? We have some weird text-based interface where you can configure some settings, maybe see how much room you have. This is more like the older version, like the old school version. Nowadays, we have a more better laptop like this here and down the book. They have some nice graphical user interfaces. They have mouse support, but they're still kind of hard to use, right? And that's as nobody understands. So what we love from our BIOS is when I press the button, the thing goes on, right? I don't care about all that other stuff. In reality, when you turn that thing on here, your CPU is powered on, and that starts in a 16-bit root mode that is compatible to Microsoft MS-DOS. So you can run your MS-DOS pretty much unmodified on your latest and greatest FOSSASIA SP Xeon system you bought yesterday. So in order to get the system in the usable state, you have to get it out of the 16-bit mode, get it in something more practical, and you also have to do the RAM, which is quite a problem. So when you start the system up, unlike the original IBM PC, you also have your DRAM. So the DRAM controller there has to be trained so that they link to the actual DIMM slots that have to be trained. So before you can start doing stuff, you have to first enable the caches, the internal caches that are the SRAM that's on chip. You can misuse that as well. But before you can do that, you have to send a sender code to actually configure that, right? Because the initial code you have, if you put the C, that would blow up by the first instruction, right? If you have it beforehand, you can't have a stack, for example, right? So we have to do an assembly start, we configure our caches around, and C goes on, and we configure the DRAM and so on. So here are the first few examples of what BIOS we could have, right? So we could have an EDK2, and this is the modern version of a BIOS called a UFI, which is a system that follows the UFI standard, EDK2 in this case. And we have more there's also Cobol, yes. And we have also the more traditional system where Cobol doesn't have UFI capabilities. But I mean, the point here is they both have to do the same stuff, right? They only do it differently. What's really interesting is that the UEFI stage has something called the driver execution environment. It sounds awful like an operating system, right? And so this is because it is one. So when we again look back at the IBM, everything came from IBM and some third-party vendors, and they put the parts together. That's it. But, in reality, the supply chain for system looks nowadays is that you have the SoC vendors, like the chip vendors on top. They produce some reference code to get the system running, for example, with the run training. They sell that, or this is constrained then from the BIOS vendors that build the BIOS, right? They take this reference code, which is mostly free, and the open source reference code that's from the Tiano Core project, and combine it with their own proprietary stuff to produce a BIOS, or at least like a framework for BIOS. And these then consumed by the OEMs, by the OEMs, sorry, by the OEMs, but bigger companies like China and Taiwan that build these things actually hardware. Foxconn is really most well known, they build iPhones and build different things. And these companies then sell it to $2 or they repackage that, put the logo on and sell to you. There's a bit simplified here because, for example, you know, that's part of their BIOS, but Dell puts their own like functionality in the BIOS. In order to do that, right, you have to add stuff to the BIOS at every step, right? You have the reference code, you have the proprietary features, codes, the building codes here, from Alliance on, and you have like the additional features from Dell. And you have to put that together. And in order to put that together, you need some kind of standard. And this is what the UEFI is. And this is the first abuse. The UEFI is actually free, so it's open source. It's mostly BSD license. There are some parts in there that are open source. For different versions, there's some free versions, but it's mostly free. Right? And this is like a reference implementation that is the basis of all the UEFIs that run in these systems. So there's already parts of the open source. Then you have things like the virtual machine. You also have some kind of firmware there because if you do, for example, Windows in the virtual machine, it expects some kind of UEFI interface. And this is pretty much completely open source. They just take Tiano Core, compile that, put it into the you have that in there. The Tiano Core project is kind of like these corporate sponsored open source projects, right? It's developed in the open. But everybody who was in there is employed by the or by a company that was told by it to contribute that. Nowadays there are lots of people from ARM coming in there, but it's still very corporately sponsored, which means that as a single developer getting the code they accepted really difficult. And you have situations where they just dump a bunch of pull requests onto the GitHub. If you don't know where this comes from, very well discussed, right? So really open process here. But you can watch at least the development, and it's all GitHub, right? You can go to UK2 pivot. Or if you actually want to happy with it, I would recommend you try the Tiano Core EBK2 platforms, which is part of the EBK plus the platforms code, meaning the code that we actually need to run it on actual hardware. Actually hardware to buy, like for example, Linux boards. But you can take this and put it and play it on thing, and it will work presumably. I haven't tried it yet. But this is like one of the options. The more popular one and the more well-known one is Core-Boot. So Core is not a UEFI. It's partly because it predates UEFI, you understand it, partly because Core has a different approach. The Core is we do only as much as necessary is to boot Linux, and no more, right? With the UEFI, for example, you have to have some drives in there. You have to, for example, if you want to network boot from UEFI, you have to have a network stack in there, but you have to have drives to talk to your network card. If you want to boot from the disk, right, you have to have disk drives in there. You have to understand file systems. You don't need that. You can just boot Linux. And this other is that code is not only open source, but it's also free software. That's GPL2 license, everything's there. It's all on the repository, right? You don't have like this separate project with like the UEFI system. And the development process is an actual open process, right? So you can participate as a single developer. There are lots of people in the common project that are just hobbyist developers, they are not employed by any company, they contribute code. The only hobby here is that everything happens with Garrett, which is group endorsed review program, and you have to live with that. But if you do that, you can contribute, and I did so. So, main short, what does like mean or mean in the code case here? So, things like the UEFI boot process simplified. So time goes from left to right, and on the bottom, the yellow boxes are like the phase, and the red is what actually happens. So we start off with some verification phase. We have the like CPU, chips on the board image, or talk about like enable RAM. And then we have the driver phase, where you have a bunch of drivers. So we have this Dixie, which is pretty much a driver package that is the UFS standard. And these drivers can reference other drivers, right? For example, if you have the network boot driver, we reference the TCP stack driver, which in turn will reference like the network stack driver, the network card driver, and so on. So these drivers are all loaded, and there will be this dependency tree that will be solved at runtime. So this takes quite a while. That's why these servers, for example, they take ages to boot. Then we have to boot manager, which will take all this driver functionality to actually figure out, okay, what to boot next. You can actually have multiple boot applications there that are loaded after each other. So maybe one is loaded and does an update, and the other one is loaded to figure out, okay, what should be next, and so on. And finally, after hours work, we finally go to the ground and drop in those villas and let it up. And all this stuff is mostly erased except for the runtime services that will remain in memory. So even after the system has completed, you still have this UEFI stuff hiding out in the RAM because it still needs these runtime services, for example, to set configurations in the UEFI. If you recall, we just take away that, but we just have the initial boot code, like December code. We do the wrong stage, and the wrong stage, it does like drop the memory trading. And then we execute the payload. The payload can be pretty much anything you want, but there's only one, right? There's not a bunch of like manager applications or whatever. You have only one payload, and most systems as well. And what we're doing is we're done, right? They know what the service is anything, you just put the system. But then tell me, kind, what we want to do in the boot. What if we want to have communicated features, right? Some people want that. But what if I want like this graphic user interface where you can configure stuff? Okay. In order to do that, like I said, we need some kind of operating system, right? But instead of writing on a new operating system, purpose built just to do booting, why not use one we already have? Called Linux, right? There are already drivers for whatever you want, wherever you want. The drivers are well better engineered than the stuff you have in the UEFI. They are more secure, right? They are more secure than the code in the UX, figuring out those with it, right? Development is very active. So just use that. Easy. When you use Linux boot, right? The idea is just take Linux, do that with the IDE with the user space. In this case, we use Huge, which is a Go program that allows you to package your singular Go application as your IDE, and Huge provides a bunch of libraries for building. For example, they can parse block configs and so on, so you can load it pretty much the same code that the block would do, but without losing actually block and stuff like that. But we package it all, we put on the flash with the code boot, and then we call it in the next place just the code just as English just as much as necessary to make it right. For example, we don't need to integrate PCI bus in our code like UEFI does. Because the first thing that Linux does after you start with is you have to use PCI bus to enable the device, but you don't have to use the device already if you're not planning to use it anyways. So just in the minimum version, which means we take off the board, we bring the CPU and the 64-bit mode, the enable one obviously, and then because Linux can use a normal system, or can use Vue, for example, to write a video application. And suddenly you can do things you why not, right? You can write your own network root system. For example, you don't have to use TFTP, you can use HTTP or something more interesting, like BitTorrent, to pull your OS package from the network. You could have a graphic user interface, right? You could, instead of having these terrible text interfaces, you could package a Chrome browser, right? It's not, right? You can have the Excel in there or whatever, have your graphic user interface done by Chrome, whatever. So maybe one case, one example what you can do with that when you use Firmware is you can build something like system transparency. So the basic idea here is system transparency is just a network bootloader that will pull a new OS package off the network, measure that, meaning it will hash the actual package, and put this into a special hardware security check where I can later query that and put that, right? Which means that I, as a user of the server, right, I can connect to the server will give me the signed version of this hash where it has been created at boot time, and send it to me. And then I can figure out, okay, is this hash value the same that I would expect given this OS package, right? So I can check the OS package, and verify the hash, and can say, okay, this has been actually boot on the system, right? So relying on people that tell me, I don't worry, this is the boot, this is OS boot here. The point being is, this is bootloader, right? And you don't have to write much code. You actually don't have to even write C code. It's just it's a bit of work with the booting, and everything else is just easy, right? Because it's a normal system, it's a Linux, that's in the flash, and we have to do now the Linux user specification to use all drivers. And this makes stuff like this pretty easy, right? And this is just one example of what you can do. So, yes, so really short while we don't have so much open source firmware and x86. The problem is actually not like the Windows and media business, or spike chip you're thinking about. This stuff is pretty much over, right? You can know how to do exactly that. I'm not going to stop you from reading anything. I'm not boot guard, right? There are lots of open source firmware systems that have boot enabled. Provides aftermarket, but it doesn't prevent you to put any open things in there. What actually happened here is that we have to borrow many of this information we need to do our NDA, and all of this like BIOS development runs very device specific, right? You have to have, for example, the board layouts to figure out, okay, how do you configure or how to set up certain ACP items and stuff like that. And yeah, simply lack of industry mindshare, right? To make a IBD in a BIOS vendor doesn't know code. Okay, so what we want to open source laptop, right? And we want it to be accessible, practical, and affordable, right? And this is where the anti-RISC-V comes in. Accessible means we're not going to flash anything, right? You're not going to buy a ThinkPad and take it apart and connect to a USB file with a bunch of wires to it to flash code content. This is not accessible. We're also not going to buy a now 10-year-old ThinkPad. It's an X230. You can buy them with code, or in this case, maybe which is a print and fork of code. This is an iRich system. You can really self-develop them. I have one of them. They're nice, right? But this is not really a practical system anymore, especially if you want to use like more stuff for like Chrome browser, for example. And the other one seems to be affordable. So there are companies that say we have a desktop with the Port 10, this is the latest iteration of IBM's Port C architecture, that's their life. The thing runs 100% on open source firmware, costs actually more than the two networks. So we are not going to use that. We simply, for example, go to buy just a Chromebook. All Chromebooks that built after 2018, they run code. They are 100% open source firmware. Google also develops all that stuff upstream, so you can just fork the code, get the code, compile it, and then depending on the device, you have to disable some kind of security protection, right? So you can just the browser can just write into your flash chip. There are some write protection there. You have to maybe disassemble the system. Maybe press the reload button combination, but then it's unlocked and you can flash your own firmware on it. Or if you don't like CoreOS, you can just get one of these. So you can have one for 606. They sell you normal laptop, one code boot, some tourism, some for custom. These are actually pretty affordable around the 1K range. They're even cheaper ones that are with the higher goals in tourism, I think. But all these, they're covered. But also, there are a lot of working on streets, or you can even build your own version of the code and throw it on there. And for servers, it's actually pretty easy. You can just go to the Open Compute project. There are industry consortium, which was initially started by Facebook. Nowadays, they have way more companies in there. So OCP is gigantic. They do specifications for all kinds of things and stuff. But among them is servers. And among their servers are the open system framework. And the open system framework says pretty much, okay, what kind of firmware do we say, okay, is open? You have to read the fine print here a bit because there are a bit more vendor friendly, in case meaning that they will allow firmware that is maybe created out of open source code, but they want to distribute the actual code, right? Only the binary and the promise that this is open. This doesn't apply to every one of those, but like I said, read the fine print. But ultimately, all the systems that is also accepted batch will likely run open source firmware. And two examples of them are the OCP service and the Tiano Plus from William. The Inspire are, as far as I know, like the latest and greatest for Rapids SP systems. And they are standard like 19-inch systems you can put it together. But Tiano Plus is a bit more specialized, they are more like 8-center type thing. Where you can have some high density Xeon or whatever, just they don't look into Xeon systems. They are fun, but they are also fun. You can put code on. The average one doesn't know that, but that's cool. It's super fun. So, takeaways. Also, firmware is obviously in the future. Nobody sells operating systems anymore. Microsoft will figure out it, but pretty much nobody sells it anymore. Nobody makes money selling compilers anymore, right? Or text editors. And this is really the same thing in less than a decade for firmware, right? Nobody will sell you a BIOS anymore. You can just get an open source BIOS, manually, change it a bit, and then put it onto your hardware. You can get a modern, workable, affordable system running open source firmware pretty easy. Just off the shelf, you don't disassemble anything, you don't have to flash anything. You can just buy them, like I said, either a Pro or a 66 system or Mono custom. If you're interested in, but I always had an idea about, hey, I want to do something with the boot system, right? I have this nice idea, I want to maybe, for example, a boot installer in my firmware, right? It said I boot my system, doesn't have no way system installed. Instead of saying, well, I can boot, maybe the firmware already comes with an installer, we pull the ISO from, the Ubuntu or Fedora, whatever, off the network, and this is all friendly, right? Some of this can be implemented super easy, right? Now that we have Linux boot, because you only have to know Linux, right? You can write the application if you write in Python. You have to know the Linux user space, right? All the drivers and everything. So if you want to get creative, now's the time. And with that, I say thank you, and any questions?
Any questions, anybody? Yep.
How frequent do we need to update the open source firmware as compared to conventional?
As often as you want to, right? So the updating cycle with Wi-Fi is maybe once a quarter, if you're lucky. If you're lucky, it's like Android phones, right? You get updates for a few quarters and then it's over. And with open firmware, you can stop updating if you want to, right? For example, the initial boot code of core boot doesn't change. You can do update schemes where you say, okay, I do maybe one version upgrade, the other one is like backup. Have this kind of update scheme if you want to do features, but ultimately you can have yourself from the follower like master and have all the latest and greatest, but always you can say, okay, this is now say right and not going to update this. That's fine. I'm sure you're not familiar with every product or project that's built on core boot. But I was kind of curious. I saw that System 76 introduced the ability to customize using QMK your laptop keyboard, right? Like you would with one of your fancy keyboards. Is that something that would be built directly into core boot, or is that a Linux boot thing? Or maybe you're not familiar with the project at all, but
not entirely, but so a laptop is a combination of a lot of chips. So you call the cable controller would be just another chip on there. I'm pretty sure that some of these controllers are probably done by systems themselves, so they're on open source firmware. I can't tell you if this is the truth for the keyboard controller, but the FI or the code does nothing with the keyboard. The keyboard is USB device, so there's no difference between keyboard or maybe a laptop.
Wait, the time he said updating is done through the what SWRT, right?
Yes.
So how do I update my open source firmware, right? So you can update with firmware, right? You can also update by just using flash ROM and flash into the system. I wouldn't recommend that because it's kind of dangerous. But if you, for example, have your own distribution of core for your own devices, you could go to the firmware team or to the US firmware service, and they will distribute your updates while you use the firmware service, and firmware team will update the systems that are out there in the field. And this is, as far as I understand, is a completely free service by that.
Any more questions? Yep.
So I don't know if you know this. I don't know if it's real or not anymore. This is how old I am. It used to be on the IBM PC standard. When it would boot up, one of the first things it would do is go into post mode. It would search a range of memory locations, and if it got a CRC check of 0 for this range, it would execute that immediately. Do you know that still exists? And if it does, then you can just put some ROMs on a PCI card and take over your BIOS. Wow, really?
I have to be an expert on this. So actually having the security side of things, and to break one of these lines, is put the proprietary one that's super easy. So there's secure boot that in theory does signature verification, but the signature verification can be omitted, for example, as that's a first in the specification, if the code comes from a secure source, like a flash. So this is broken. The secure boot that hands off to the bootloader is also broken because there's something called the machine reading board that signs the shared bootloader between secure and block for the US distributions. They will sign pretty much everything, including things like the IPC logo that loads everything. So this is also kind of broken. And then there are people like Alex Microsoft that do actual code analysis of these proprietary verifiers, and they dump like 10 CVEs per conference talk there. Like in a few weeks, there's the folks back in Asia, and they're going to have another like 20 or so. And this is like code not necessarily just in the build process, but it's also code in these runtime services. So this is how we talk about that there is still code running in a specialized, high-privileged system mode in the CPU, but it's still accessible after this is computed, and even that code is broken. Getting it is rather easy. So yeah, there are lots of things to explain in this system. And if you have, for example, a PCI card, there is something called optional that the PCI card supplies to the BIOS, and it will be executed as part of the boot process. It is signed, but not it's secure. It's not really that secure.
All right. If there's no more questions, thank you, Kai. Okay, with that, here you go. Sean, it's all yours.
All right. Thanks for coming. Hopefully this all works. This talk is going to be on the state of open silicon. And if you want, you can follow along down at the bottom, p.zobs.io/FA23. So a bit about me. Hopefully that's working on the stream. I work on hardware projects. I started out as a software person, but I kind of moved down and down into the stack. We're working on the precursor secure communications device, which is FPGA based on RISC-V CPU in there. FarPatch is a project I've been working on, and I might give a talk on that later. It's a Wi-Fi debugger that's ESP32 based. And FOMU, possibly the smallest FPGA development board, it fits in a USB port. But today we're going to be talking about open silicon. And this is not correct. Okay. Okay.
I think you're controlling. Press stop. Okay.
Okay, so this might not work as well because this presentation system isn't. Anyway, software is hard, it turns out, and silicon tends to behave a little bit better at times. But overall, this talk is going to go on what it means to be open, because silicon as a topic is something that a lot of people don't really know about. So the concept of what is open silicon requires a rather lengthy amount of discussion. What can we do today with the current state of open tools? What can't we do today? And where can we go from here? So to begin with, what does it mean for silicon to be open? Broadly, there are 4 things that need to happen in order for a system to be considered completely open. For starters, we need manuals. If I give you a piece of silicon and there's no manual whatsoever, there's not much you can do with it. So you need to know things like characterization. What voltage does it run at? Where the debug pins come in? What does the memory map look like if it's a CPU? We need the source code to the CPU, which includes things like the Verilog or the VHDL or the Scala that went into actually defining the CPU. Even if you can't do anything with it, even if you just have the source code, there is some value into seeing how the CPU is built. As example, there's a chip called Propeller, which has like 16 cores in it, and they actually produce the actual release the Verilog for the CPU for an actual physical chip you can buy. Also important is the tooling. Proppy spoke earlier about the open lane flow, but if I give you a piece of silicon, if I give you a C program and I don't give you the compiler, there's not much you can do with it. So it's important for a chip to be considered open if you have the tooling to actually do something useful with the source. And finally, the GDS2. How many people here have ever built a PCB? A good chunk of hands. How many people have ever made a PDF file? A Gerber file is a PCB. It is the output that you send to the PCB foundry. A PDF is a file that contains everything in the Word document or the simple Office document that you made that you send to somebody else. It's going to be the same regardless of what platform you're on. GDS2, sometimes called GDS, is the file that you send the foundry that they will then turn into physical silicon. So if somebody has a GDS2 file, they have everything they need to give the foundry to copy the chip. And this is some of the most rare stuff when you want to make an open chip, because it means that anyone can just clone it. So in terms of chip design, there are more or less 4 different steps to making a chip. For starters, there's non-disclosure agreements, which are required because the foundry has put a lot of money into building their tools, and they don't necessarily want the competitors to know what they're capable of. There's also a lot of other characterization that goes into it, which is the process design kit. So this is when you make a silicon chip, you run it through hundreds of machines, and each machine has a different tuning, and the actual tuning of the machine means that the output will have slightly different characteristics, and that is all very proprietary for each individual foundry, and that is resulting in a process design kit. This is an example of a stack up. So what this is 5 metal layers in polysilicon. And so with this, you can tell that at this particular foundry, this is what the different layers are. And so this is what you have to work with. On top of that, you need software to actually generate the tools. This is that tool that goes from the source code to the GDS2 file. And it consists of a bunch of different things: synthesis, power generation, clock tree synthesis, place and route, verification, simulation, and a whole bunch of other things. The thing is, this costs $1 million per seat per engineer. So this is completely cost prohibitive to any sort of open source project. And if we want to be able to make our own chips, we're going to have to replicate all of this in order to have an NDA-free and open process. Now, I want to talk a little bit about synthesis, because that is the first step in here, and that is the side of this tools that users most directly see. I'm going to talk about them in a little bit, but first, IP blocks are another thing you're going to need to build a chip. When you write a program, you go to Node, NPM, you go to Cargo, you pick up a library. For example, if you want to do a JSON parser, you don't want to write a JSON parser. You want to get a validated JSON parser that does what you want, because you really want to build something that is doing your processing of a post or something like that. You don't necessarily want to be in the business of writing JSON parsers. In Silicon, it's the same way. We go to IP blocks, which are kind of libraries of pre-vetted, tested silicon blocks that you can just drop on your chip like a library. An example is a PCI Express controller, which is it's a really complicated piece of hardware. It's a lot of timing, SERDESs, all the configuration that needs to go. Radios are another example. If you want your chip to have Wi-Fi, then you're going to need to get that tuning from a library vendor who hopefully has tested out in the particular foundry you're working with, so that it's guaranteed to work the first time. And then there are standard cells. And these are the tools that most people interact with, although they don't know it. So I am going to go in a little bit about standard cells, but first, a quick side detour on Boolean logic. Think back to your secondary school. You have Boolean logic is what underpins most of the CPUs, most electronics, most digital design these days. You have your P and your Q on the left side, and you have all these gates. This is a truth table. Basically, it is a piece of silicon that has inputs on one side and defined outputs on the other side in a combinatorial fashion. In the old days, way back in the 1970s, when you designed a chip, you would design it with a pen and a piece of paper and a room full of people just sitting down for weeks designing each individual transistor. They would design each of the metal layers by hand, and then they would image it and project it onto a piece of silicon. It was very time consuming. You couldn't scale it very high. This thing's only, I think, about 10,000 transistors. And if you make a mistake, it's kind of a big deal because you have to erase everything and start over again. So it was fine in the 70s. It was becoming kind of fell out of favor in the 80s. Nowadays, we do chips like this. This is a GD32 gigadevices, a relatively modern ARM chip. And if we look at this, you can see we have, these are the sections of the chip. We have memory in purple there. Those are all IP blocks that came from either a foundry or an IP vendor. And then we have logic on the side. And you can see we call this kind of a sea of gates type thing. All of this logic here is code that was written by either a human or a text generator or a code generator that is then compiled down using a synthesizer. So when we say we design a chip using Verilog, this section right here, this purple section right here, is all of the logic that is resulting from writing Verilog code. So the synthesizer, you can see, is generating a third to 2/3 of this chip, and it's a fairly big section of it. Zooming in, if you were here at Poppy's talk, you would have seen something like this in the generated code. This is zoomed into that logic area, and you can kind of make out these vertical tracks where they just line these standard cells up one next to each other, and then run the wiring. So when we do place and route, this is what it looks like in real life. There is a real life consequence to what we do. And if we strip away another area of metal, you can actually see this is the low polysilicon layer. So this is what it looks like in real life. So today, we do something like this. Rather than wiring up transistors by hand, we do a Verilog module like this. This takes input A, B, C, D, outputs X, and the actual mathematical operation we're doing is A and B and C and D. And the job of the synthesizer is to take that and turn it into gates. It may be that your standard cell library that you got from the foundry or whatever has 2 input ANDs, in which case the synthesizer would do something like this. 2 AAB get ANDed together, CD get ANDed together, the results of those get ANDed together, and you get your output. But it may be that your foundry has a 4 input AND, and so the same synthesizer would take those inputs and AND them all together in a single step. So in this sense, the process, the standard cell library provided that you're using has a direct impact into what the synthesizer goes and does. Also, you could put both of these in the standard cell, in the digital design section. It's whichever one happens to be fit better. Having said all of that, now we get to the meat of this. Where are we now in open source? Well, things are actually looking pretty good. Non-disclosure agreements, we don't have to really do them. Everything here is up on GitHub. Everything is freely available. You can download it. No NDAs required. For open PDKs, we actually have quite a few. We've got Sky 130 and GF 180. These are primarily so Sky 130 is from Skywater in the US. GF 180 is from Global Foundries. That's 130 and 180 nanometers respectively. SG13G2 is from Austria. That's a relatively new one. And we have this interesting thing where we actually have fake PDKs, PDKs that don't actually correspond to any particular foundry. This is kind of an interesting artifact of how, remember I mentioned that everybody in all the non-disclosure agreements are important in design. If you're publishing a paper as an academic, you need to be able to have reproducible results, but you obviously can't publish the PDK because it's completely proprietary. So they have fake PDKs that they generate that you will see used in papers. And these are kind of a stopgap that they've invented to get around the fact. Well, the great thing is we have real PDKs we can use now. So this is going to be a boon for academics because it's no longer just a fake thing they're doing. They can actually use real PDKs. For hardware synthesis, if anybody's done any FPGA work, you will have used YOSYS in the open source world. YOSYS primarily deals in Verilog, which I showed earlier. There's also VHDL, which is handled through a plugin called GHDL, and System Verilog, which is what a lot of microprocessors are written in. is supported as well. In terms of placement and routing, this honestly produces the prettiest pictures, so if nothing else, it's good for that. Placement, routing, power distribution network, clock distribution network, this all comes from a tool called Open Road that basically exists to take existing projects such as OpenSTA for static timing analysis, and it pulls them all together into one very pretty looking GUI. In this case, you can see the lines there are the clock tree in this particular chip. As for inspecting the output, you have your PDF viewer to view a PDF. We've got K-Layout and Magic, which are capable of inspecting the resulting GTS file. And this is a chip that I routed, and you can actually see, again, the lines of standard cells in here. It's taken all of the logic from this particular CPU and stuffed it into lines that are filled with those standard cells. And as for available IP, that's one of the other things we needed. Thanks to the Open MPW project that Google has sponsored, there is a lot of IP available. So we have CPUs, we have the FPGA that you mentioned, those mentioned earlier, we have SPI, USB, crypto accelerators with like AES. We have some analog IP for things like analog to digital controllers and phase lock loops. So those are all available as well. For standard cells, we actually have a few different flavors. We've got Sky 130 from Skywater, we have GF 180. We also have this thing called OSU 018, which comes out of Oklahoma State University. And we also have Libre Silicon, which comes out of, I believe, Hong Kong. And the interesting thing is you can use these standard cells with other process design kits. So we've actually had OSU and Libre Silicon taped out in global foundries. It's great that we can do this, but there is a lot of stuff that we can't do today. Memory is still rather hard. The density is improving, we're getting better, but for a tiny 3x2mm chip, you can expect a few kilobytes on the chip, which is kind of unfortunate when you compare it to like modern CPU where you have megabytes of cache. We just can't do that yet. The hope is over time we'll get better density, and we do have experimental ROM support, which should remove some of them, should shrink ROMs down somewhat. But here's kind of a sad example of this. Here's a CPU I did with, you can see the registers are, the memory is everything in red, and the CPU is kind of that block right there. Now, to be fair, this is kind of a contrived example, because in this case, the CPU was designed to be small, and these memories are all 5-volt tolerant, so this is kind of taking it a little. But the point is, memory is still really hard. Having said that, the Open RAM project is designed to pack memory as tightly as possible. And oftentimes memories actually violate the design rules because they're regular enough that you don't have any interaction between nearby transistors. And so this is an example of just 16 kilobytes of RAM at 3.3 volts on Sky 130 from the Open RAM project. Non-volatile storage is also a bit of a problem. We don't have anything like flash or EEPROM. Sky 130B has resistive RAM, ReRAM, which is still somewhat experimental. There are modules you can put down, but that is specific to Sky 130. It hasn't yet been ported to some of the other platforms. Kind of the solution that we're working with now is just use an external SPI flash. I mean, this is what a lot of processors use today, actually. Gigadevices and ESP as chips don't have on-chip SPI, on-chip flash. They all use external SPI flash. So it's not really a problem, but it is a thing to look out for. The other issue is that I've mentioned Sky 130 and GF 180. These are relatively large nodes. Wikipedia has this great section on what designs were common on these nodes. The PlayStation 2 was at 180 nanometers in the great year of 2000. The GameCube was in 2001, was on 130 nanometer. Having said that, the GameCube and the PlayStation were really great machines. They did a lot of interesting stuff. So even though we're not on the latest 5 nanometer process, 3 nanometer process, there's still a lot we can do. There's still a lot of work to be done. There's still a lot of value to get from these large nodes. And in fact, just because it's a large node doesn't mean that it's a bad node. I mean, here is an LED flicker. This die shot is again courtesy of Zepto bars. This is a digital chip that basically simulates a candle flicker. It's all, you can see again the tracks here are the digital logic. This is 3,000 nanometers, 3 microns. So you don't need a super tiny process to do something interesting in open silicon. You may not make the latest and greatest fast processor, but you can still derive value from it. One of the other issues is that analog IP is still a little bit difficult. We have a lot of work on the digital section, but unfortunately analog is still kind of an unsolved problem. We do have some ADCs and PLLs, there's a band gap generator that somebody did, but it's still somewhat difficult to integrate that into your project. There are various projects to solve that, such as FuseSock as an example of an IP curation project. But analog IP is unfortunately still one of the blind spots in open software, or open hardware. And of course, the elephant in the room, taping out chips is still kind of a problem. Google occasionally does OpenMPW runs, with the caveat that any design you put on OpenMPW must be released as a fully open project. If you don't want to have a fully open project, you want to keep your IP closed for whatever reason, other companies, ChipIgnite, Europractice, Muse, SIMC, and plenty of other foundries run multi-project wafers where they amortize the cost of one wafer, which is several $1 million, across multiple projects. But even so, it can still be $10,000 to $50,000 for 10 square millimeters of silicon. So if you can get on something like the Google MPW or OpenMPW, or hopefully we can find somebody else who would be willing to fund this in exchange for getting open IP. But for now, unfortunately, this is the reality. So having said that, where are we going from here, and how can you help? Well, the hope is more open projects. So this is a screenshot from one of the OpenMPW projects. They run occasionally. I don't think there's one open right now. But if there is one, you can help by getting in on it and learning more and submitting a design to grow the pool of IP that we have. Education has benefited a lot, and so education will be getting a lot more with the open tools. I know I was speaking with some academics who were running entire courses using the open road, open lane flow. And one of the nice benefits they had is that they didn't have to have their students sign an NDA. Normally when you're running a classroom, you have one machine that is running some version of the proprietary vendor tools, and everyone has to connect to that, which can be rather challenging when you're off campus or when everyone's accessing at the same time, running their place and route synthesis at the same time. So allowing students to run the design tools on their machine with a PDK that they can get without any NDA has been huge. There's also the tiny tape out project that was mentioned earlier. They divide one of these chips into 250 sub chips. And so for $25, you too can get an area on a chip that's about 1,000 gates. So you can design, you can see little tiny strips of cells in here. $25, it's a deal for your own chunk of chips. It's also part of the Zero to ASIC course, which is another resource you can go to if you want to learn more. And I'm hoping we can get more analog design, because there is a lot of interesting things you can do with digital. There's simulators, there are generators for digital, but analog, again, is still somewhat of a blind spot. So if you want to help learn more about analog and create analog IP, there's a website called SillyWiz that has a lesson plan that you can use. This is actually an example of a PDK running in the browser, where you're actually drawing on a GDS, virtual GDS file, and it runs a physics simulation in the browser. And it's great because you can see in real time what changes get made. this change will affect the voltage in this way over time. Hopefully that someday we get a smaller process from open node. This is more wishing. Open NDA, Open Road has been tested on smaller process nodes. They've taped out on Intel 22, they've taped out on GF1, GF12. But unfortunately, there's no deep sub-micron NDA-free PDKs yet. Sub-micron is anything under 100. It would be really nice if we had an open PDK that was 45 or below, but unfortunately, we don't have one yet. So hopefully, we can convince some foundries that Skywater and Global Foundries have released their older nodes. They haven't gone out of business yet. Hopefully, we can convince them that some of the smaller nodes are worth opening up so we can actually have smaller PDKs to work with. And finally, just more involvement. Get involved in the Open MPW, do a tiny tape out, learn about SiliWiz. Just we need more people to realize that this is now an open section of design, and you too can become a chip designer thanks to these open tools and make pretty pictures. So thanks. Any questions?
Questions, anybody? No.
Not a question, but a comment. I can suddenly see a reason why I might want to get involved. Not Gates, the animal question, definitely.
Is any of this, now that people play stuff, making it work, people are going further along or doing new things with multiple clocks, doing async stuff? Is there progress being made on that area? I know that was like a really hard area for people who play with FPGAs.
Ooh, async. I'm not aware of any async CPUs that have been done in any open tools. I know that many of the simulators that exist, for example, iVerilog, which is one of the Verilog simulators, gets really unhappy with a lot of async stuff. Verilator just gets rid of it, so it doesn't simulate it at all. You would need to use something like Spice, which does exist and would work just fine, but I don't know of any Verilog to Spice. It would be challenging to get working, and I don't know that anybody has, but the tools are all there if you want to feel like loading them together.
All right, if there's nobody else, thank you, Sean. Thank you for the session. I think good pictures and the last one.
Good afternoon, everyone. And next I will introduce our
mic, please.
Get the mic. I will introduce our practice and the experience of overheating on this file. This talk will be done by me and my two partners. And first, let's introduce myself. My name is Jianfeng Li, and Hansen Feng is my nickname. I know what you are thinking. Alright, I'm not Hansen. I started working on Linux distribution in 2014, and then become overheating developer and development maintainer. Now I'm the overheating technical committee member and with 5 SIG maintainer. Overheating community is an open source community based by many people from different places. And we are maps to build an easy to use desktop operating system. The image on the right is our UI of overheating, which has desktop and tablet modes. And suppose running on x86 R and RISC-V architecture. And below is our homepage. You can go there for more information. RISC-V is an emerging open source instruction set architecture. It offers numerous benefits, including flexibility, scalability, and security. Our team is dedicated to exploring the potential applications and contributing to the development of this technology. Our team has many RISC-V versions involved, including escape writer and deep computing, star5, T-head, Tiger Lake, and so on. This is the framework of our work on RISC-V. For the hardware, we choose Hi-Fi Unmatched, Vision 5, and Xuantie. In the kernel layer, we adapt and optimize according to the hardware characteristics, including power management, graphic display support, computing library, and so on, to improve our performance. Also, we built an easy-to-use desktop environment called named UKUI to give users a friendly experience. And for the application, we create an application compatible way based on QMU to enrich the application ecosystem, in which the application of x86 architecture can run directly on the RISC-V architecture. And this is our main platform architecture, from source code to package compilation, to image generation, and to unit testing. Those management and translation management are also connected to our Git repo. We try to automate the process as much as possible, including automated code uploading and automated testing of daily images. For RISC-V related compilation work, we mostly do it based on QMU due to the lack of devices. Since the end of last year, we have had almost 300 RISC-V packages compiled successfully. Our goal is to build an open-killing RISC-V version, which with a rich software ecosystem and seamless user experience. To achieve this, we are heavily focused on hardware platform, adaptation, and the software ecosystem. Next, my partner, Dr. Wang, will show our specific work in those areas. Good afternoon, everyone. My name is Wang Wenzhu, and I'm from the Hacker Library of Information Technology and Application Innovation in Tianjin, China. As a member of the OpenKV Technical Committee and RISC-V stakeholder, I'm thrilled to be here sharing our work with you. My teammate Li Jianfeng has already introduced the work of the OpenKV community, which covers software compilation and system structure. In my part, I will elaborate our other work initiatives related to RISC-V. First of all, let me talk about the hardware adaptation. RISC-V is a new and promising ISA architecture, but it also faces some challenges due to its early stage and lack of unified standards. This makes it difficult to adapt operating system on different RISC-V hardware platforms. Therefore, we have been working to make OpenKV compatible with various RISC-V devices and ensure optimal performance. The first is to improve the power management module. This involves modifications to the device tree of file and the kernel driver to enable the operation and of the power management chip. Then we can perform device shutdown, restart, and other functions. Secondly, we are working to optimize the system startup and reduce unnecessary service items. This ensures faster boot and efficient reduce the boot time. Yes, thirdly, we configure the operating system environment to ensure the normal use of like a screen displays, network cards, and the USB devices. Okay, as we all know, GPU is a key factor that impacts the user experience. Therefore, we have developed a complete GPU software stack to provide a seamless user experience. The first component is the driver in the Linux kernel. This driver controls the GPU hardware device, managing the input and output of computing tasks. The second component involves adapting and calling GPU-related libraries, including Mesa, GStreamer, LabGL, and other labs, which are essential for GPU. Thirdly, we have completed the adaptation between OpenKV UKUI and the other software to ensure the normal use of GPU in desktop environment. Finally, user mobile applications such as video playback and web browsers are modified to utilize the GPU library calls. This results in higher performance and better vision experience for the user. So building a rich software ecosystem for RISC-V is another key task that we have been actively pursuing. Firstly, we have created a suite of tools and resources aimed at helping developers use RISC-V more easily. These include the comprehensive RISC-V toolchain that includes compilers, assemblers, debuggers, and other essential components. Additionally, we have created a software library that provides
a range of calling functions and modules for RISC-V-based systems. This library includes various drivers and utilities that enable quickly leverage the functionality of the RISC-V hardware. Also, we have built the basic user applications such as Firefox, LibreOffice, FFmpeg, and OpenKDE software, which can meet the basic needs for the daily work. So finally, we have established the document and the support channels to help developers learn about the RISC-V and address any problems they may encounter. Another way to enrich the software ecosystem is binary translation. This allows application designed for one SA to run on another SA device. For example, iPOS Rosetta 2 enables M1 and M2 chips to run x86 applications. So there are also many open source projects that can achieve cross-platform software compatibility. In OpenKDE, we're also working on this area, trying to make x86 applications compatible with RISC-V. We have mainly used two techniques to improve the performance, including local library wrapping and dynamic block caching. Local library wrapping is necessary to translate library files from the source platform to target platform with translation or without translation overhead. This allows the platform to directly call the APIs of the local library, avoiding the translation process and greatly improving the system performance. This is the dynamic block caching. It's another powerful technique. As we all know, a small amount of code is executed for the majority of the time, such as the while loop and the for loop. By catching translated code, we can avoid the need to retranslate them each time. So instead, we can use the previously translated code, which saves time and improves the overhead system performance. Catching of code blocks can be implemented using different strategies based on specific application scenarios. So finally, let me briefly introduce version release work. It is very important to make OpenKDE accessible and available to as many people as possible. Since we released the first OpenKDE version 0.7 on July 2022, we have updated 4 versions, each of which fixed the previous bugs and adds some new features. For example, in version 0.7, we supported VLAN and adapted OpenKDE's self-developed software. In version 0.7.5, we improved the system stability. In 0.9.5, we provided the latest UKI desktop environment. So our goal is to make OpenKDE on RISC-V a robust desktop operating system that can be used by a wide range of users, from desktop enthusiasts and developers to researchers and artists. So far, OpenKDE can run on 5 RISC-V platforms, including HiFiMH, Vision-V 1 and Vision-V 2, T-Head, and also the Cumin. So the total number of downloads for all versions have reached 14,000 in under a year. from July of last year to now. And we hope to see an increasing number of RISC-V users in the future. Now I'm very excited to introduce Roma, the world's first laptop that comes with OpenKeying pre-installed. We have equipped the system with basic application software and development environment to provide a great user experience for enthusiasts and users. So let's please welcome Mr. Liang Yuning, the founder and the CEO of Excalibur, who will introduce the Roma laptop to us.
Hi everyone. Thank you for a great introduction on the OpenKeying stuff and great stuff. And I tell you the story why I started to making the first laptop of my life. You know, I run a software company called Excalibur. We used to make compilers based on Open64, and we decided to make a laptop and to try to get it mass produced from a software guy like me and see how hard it is. It's quite hard. So, and this is the reasons. The reason is that we want to have an experience of x86. We can carry it around and play with it, and we can compile this by code straight away. We don't need any cross compiling. And a lot of project open source is not supported cross compiling files anyway. So, and I want to try the latest this by SoC in 12 nanometers to see how many problems in manufacturing and especially mass production. I met a lot of problems, especially in 2022. The whole COVID things in China is in the mass. So, and this is the quote from Mark, RISC-V International. It says, "Yeah, if we can get native development now, we can accelerate RISC-V software ecosystems, OpenKeying, more libraries, and so on and so forth." And look at our laptop. This laptop is the thing is I can do, and we'll try it hard, try everything hard, right? And it will support now OpenKeying and possible Chrome OS in the future soon. And we make some speciality. For example, we spend a lot of effort in recycling stuff and making the box and like the stand. And we make a very special hotkey called strike key. And let's get rid of Windows, all right? So that's the point. And yeah, you will see if the window can zoom in here. So let's see whether we can wheel make it bigger. So I'm not sure you can see, but anyway, you can see this is a real RISC-V things, right? And running on. It's not joking, okay? So let's see the R key, see whether it works. Remember R key for what? On browser what? It takes a while to pop up. So you can see it's very buggy, very slow. But the point is that why we have to make the first step. Just 9-10 years ago, when ARM has the first 64-bit, is far worse than now, right? This is the first 12 nanometer 64-bit SoC. So and it's not in my experience. I put the first ARM 64-bit on Android. For Huawei, so I know all the painful things. I think now RISC-V 64-bit with that kind of performance is far better than 10 years ago. So we look forward to another 10 years, and RISC-V will go beyond much quicker than now. That's all. So this you can see the browser is here. It's very slow, very buggy. So and we get better. And especially in May, we have a mass-produced versions, so a lot more stable, the software a lot better. So you look at now, this year, we try 12 nanometer, you will see we might have a mass-produced problem. Probably might not be going through the stress testing, heat testing, all the stuff, but the 22 nanometer is fine, perfectly fine. And we will looking forward to the end of the year. We support 64 core, very thick laptop coming out, purely for developer carry around and with a big fat battery. And you can turn on and off all the cores, whatever you like. But that and we look forward to Jim Keeler to roll out a very big fat IP coming out and probably 7 nanometers. So we look forward to all the trend. And of course, and we're gonna cooperate with OpenKitty with a lot of programs on the user the community program. So we are going to do some reward for all the people contributing back to Kitty and our hardware products. So and that's the painful things. I use the thing is laptop structure and with the highest performance 12 nanometer first ever in making a laptop with a software guy and no experience. The painful comes. Right, and we gone through. You can see this is the pictures that the SoC not designed good enough for mass produce, and we need a very high precision soldering. Just like mobile phone. But mobile phone is a lot high volume, and I can't book the capacity at all for just doing the soldering on the board. But anyway, we get it done by get it around by some help good friends. And this is our motherboard. So the motherboard, we have we call it SOM module. We can plug it in, and the motherboard we're going to reuse. We're trying to reduce, especially after a while, we have our own chipset coming out. The motherboard won't change, but the SOM will change according to the SoC upgrade. So it's a very ambitious project, but it's a very painful. But like Peter, been chasing me for fun. But we're getting there, and we will get there. And yes, we will open source our motherboard, so everybody can take a look and how to make a laptop. Very easy, very simple. Now, from our experience, we can say that 8 to 10 weeks we will swap a new SoC, and we can mass produce 1,000 laptops that quick. And we will going to have hopefully in around June we're going to have a bootstrap reward program. All the money coming from Peter, we're going to reward back to the market. So whoever help us making better product for RISC-V or OpenKitty, we're going to reward them, right? So and yes, we have a very good relationship with OpenKitty, hopefully, and we can run a very good international version of OpenKitty. We're exactly the same as Ubuntu or now. Right, that's our goal. Thank you very much.
Thank you. Questions? Anybody?
Any questions?
Here you go.
So yeah, so I got one of the original RISC-V chips that was ever made when they did the thing going, and I'm kind of curious, like, where are you seeing compared to like the ARM is good progression, right? How do you feel like it's going to come out as far as power versus performance as it evolves?
From the hardware side, I would say that is a chicken and apple, and the power and performance always a triangle balance, and I would say hopefully the battery. If I say that we're trying to compare x86, and I would think it's better, but if for ARM, I don't know. Right? In the short term, no. But you give it enough time, 3 to 5 years, and might be
Yeah, of
possible.
course. Yeah, you need time to evolve.
And the point is that we need the one thing now, all the SOC company got a problem, they always come to produce a development board. It's not the final product. That makes the growing is hard. You got to go into a mass product no matter how crap it is. Right? So to move it evolve quicker. Otherwise, everybody waiting, just showing off the development board is not gonna help. But you got to test the market. And if you fail, then you make it better. You know where the better at the moment. Development board can't tell you where it's better, where's good, where's bad. That's my question. Hopefully I answer your question.
All right, more questions in the back?
Hey, it's really great to see another open laptop. I'm curious about the case and the shell. Is that something that you've developed all the ID yourself, or is there a library that you can go to that gives you things like the screen and the touchpad and all of that, you know, like a standard display connection, things like that?
And I would say that all these in southern China, the Bay areas, they have a lot of we call it common mode. Like basically, is that you can pick off the libraries, and then people can just mass produce it with no copyright and blah 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 whatever it is. And there's some fancy things, there's some untested things, and like this one actually is mass produced in x86 and in the latest i7, and this year from i9 with bigger screen. So we use the tested version of it, the structuring, and we just changed the board to this type.
Does that mean you're thinking of doing it again?
Yeah. You're welcome. But basically, I would say that anything help this type move quicker, and whoever ambitions, then quickly. That's why I gone through all the painful experience, and I don't want the world to meet it again. That's why we open source it.
You mentioned that you're going to mass produce soon. Will this mass production will be serviceable? Will it be DIY friendly? Will it be easy for me to replace the screen, replace the battery, change the keyboard?
And I think we will mass produce this one, and if the screen and all these things, as long as you fit in the structure, that's possible. But if it's not, then it's not, right? It's not a modular, it's not a full modular design yet. When I look at in Chrome and Google, they do design make a modular Chromebook. But the problem is that when you become modular and the price go up in the mass produce. For example, the 22 nanometer, we're looking into going down to $500 US dollars. Right. And the BOM, you know, besides whatever the overhead, whatever you're running a production line up to whatever, you know the BOM. So we have to leverage the common use. So we share a lot of components with x86. Otherwise, you won't get that chip at all.
All right, another question. So we can do that. Are you familiar with the Firmware laptop? Have you seen what they're doing?
Yeah, I heard about it, but it's not going to get the price down. Yeah, the supply chain is where you have to reuse components as much as you can. Yeah, otherwise, you're modular, but you know you module with nobody. You module with your own self. Honest. So you have to be sharing. Share as much as you can. Yeah, and take the fancy structuring and change it and share as many components as you can, and that will make it better. And at the end of the day, the laptop, the battery, basically the motherboard thing is never change, except Wi-Fi. Go quicker, Wi-Fi 6, Wi-Fi 7, anything else never change. So there's no point you keep changing a laptop for the motherboard at the end. So that's why we call it, we try SOA modules. Hopefully we get it.
Yes.
How supports extension paper, standard USB and HDMI?
Yeah, everything on x86. We support. HDMI, Type C, blah 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 blah.
I see.
Yeah.
I see. That means
USB.
display port and
Yeah, everything.
analog audio
And everything. Same as your mobile.
Wow, fantastic.
Yeah.
All right, there's one more question here.
You mentioned about this is a 12 nanometer SOM. So that also by your team, the chip itself?
No, not the chip itself. The chip we're using Starfire. We will use all the SoC on the market and try to make the engineering versions. You know, like crazy guy like Peter, we will ship all these crazy things to him to test it. Right. So it just, to be honest, RISC-V isn't ready for normal users. But it's ready for the developer. The crazy developer have a dream about RISC-V and grow bigger, you know, in 10 years time, like us. That's it.
All right, I'll take the last question here. Me.
It's all about pure kidding. Why don't ask me anymore?
Why is it called Roma?
Oh my God.
What's the backstory?
I remember
I'm reading here.
You know, originally, I'll see whether I can open this, my PPT.
It's gonna take a while for it to start, right?
Yeah, this net is still bugging.
I know, but I will not say.
Oh, you won't, he's not gonna say it.
You know, so bear with me, it's very slow. What you expected, a baby just coming out from the.
When was this machine made? When was it actually manufactured?
We actually got it all working functionality just in 2 months after the Chinese New Year. So before Chinese New Year, China is in stable state. You know, you can see it's very slow. You know, so it's. Roma. You know what Rome, right? Yeah. It's an empire. Right? No. Net. I don't know whether you can connect it. I don't know, but you can try. You can feel free to try. Right? Why not try it? If we break it, we break it, right? Where am I to be put it though? You need a lot of hope. Come on. Come out. Oh, where's the
Rome is a building.
Okay. So Rome can be built in one day. And Lord, can you stop? That's the reason. And the other reason is Rome is the destination we want to go. And there's many paths we can reach it. That's all.
选度实际是你的公司的名字。
Probably, yeah.
The deep computing is company name.
Deep computing is the guy. Is the guy, the guy behind this company is one of the famous guy industry, the shareholder behind deep computing. He knows a lot of guys making laptops and pad and whatever. And he's the guy paying for all the prototype and everything. It's a very entrepreneurial chipset guy. He makes chips. And me is a software company in charge of all the systems. And
Unfortunately, this time we travel to the hardware, so you can see how tricky it is. Thank you.
Thank you.
All right, thank you very much. Thank you very much, everybody. And with that, we end day 2. So, yeah. So come back tomorrow.
Thank you.